So this lecture is going to be about sort of the general issue that you have. We've been talking about synchronization, and we talked about two very simple synchronization primitives upon which you can build many other much more sophisticated ones. And I wish we had enough time to go through them all, but we just don't. And so what I want to do is talk about a specific issue, and we'll illustrate it with an example, and then we'll show a really novel way of solving it that's actually becoming so widespread that it's really helpful to know about it, and it'll actually, it'll be really neat if you walk into a place to do systems programming and you actually know about this, because a lot of people don't actually know about it. Okay, so yeah, mutual exclusion, blah, 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 we talked about that. There's a lot of examples of shared state in the OS kernel, and often it's managed in linked lists. It isn't always. You may have trees. The Linux scheduler actually uses a tree now. You may have many linked lists, which you sort of move things between if you have a multi-level feedback queue mechanism or something like that. Hashing is also frequent, but hey, if you have a linked list of bins in each hash bucket, then you might end up still with linked lists again. Okay, and the other thing that's really common is that the state is read. It is read a lot more than it's written because the OS needs to look things up and decide what to do. It's not actually modifying it. If it had to write all the time, then the mechanisms we're going to talk about today would actually be pretty annoying. Okay, but there are a lot of examples of shared state. Processes are managed in shared state. File system cache. We'll talk about the last two a lot more when we get into how those things actually are implemented or how you would design them. So anyway, but because we have a situation where we have a lot of things in these simple data structures and they're read a lot, we have some interesting things that we can do. So the question is, how do we implement a linked list that supports concurrent access from multiple kernel control paths, and we expect that we will mostly read it. We will write it much less frequently than we read it. So we have a simple example here. Okay, we have a list node A and B. Who cares what the values are? We really don't care. Presumably they have some meaning. And then we have a pointer to the next node in the list, and we have an anchor to the list that's pointed to with head. Frequently you would also have tail. You'd probably want to have a doubly linked list so that you could go backward as well as forward, but we're just trying to distill this down to the simplest version of the problem. Okay? And so we have something like this. The head points to the first node, blah, 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 all the way to the last node has next is 0. Okay? So this is our sort of our context, and we have various operations we might need to perform. We need to look at all the elements. Maybe we need to look up a particular node. We need to find the node with A is 9 or something like that. We need to be able to insert a node into the linked list, either at the front or maybe at the back or maybe at some specific position. We need to change the contents of a node. So we're not just destroying it, we're just changing its contents. And then that's all we need to do. We need to remove a node from the list. And I think we all know how to do these things. If you don't, then you probably shouldn't be in CS124 because that's like really bad. But all of these things are very straightforward to us at this point in our programming careers. But then you take a look at this and say, okay, what about in the context of concurrent access? What about in the context of concurrent manipulation? That's where this starts getting really interesting. And if we didn't do anything about synchronization, we didn't do anything about managing shared access to this thing, it would be pretty quick that our thing would become corrupt. Now, if like 99.9% of the time we only read, then we might not see that corruption right away. We might see it after the system runs for a while. If we had like 60% of the time we read and 40% of the time we write, then we'd probably see the corruption right away. So we have T1 here is our first thread traversing the list. It's got a pointer to a node. Notice it's pointing to the first node. And it's looking for A equals 12. So that's obviously going to be toward the end of the list. And another thread is inserting a node into the list. Okay? So clearly, depending on how we do this, we can run into huge trouble. And part of the reason why we can run into trouble is we could probably specify a sequence of the sequence of the operations we perform such that threads don't get confused, except that we have reordering at both the compiler level and we have reordering at the processor level. Okay, so yeah, several operations. These are going to be our simple example. So new A is 51, new B is 24, next is P next. So we just go ahead and say, you're going to slot in after Yeah, after the node that T2's P value points to, and then P arrow next equals new. So we go ahead and stitch it in there. And we can try to do this in a way, you can see that the order that I have it probably is the most reasonable order, right? So P arrow next doesn't actually change until we're all hooked up and ready to go. You can imagine if we had some other order where we said, P arrow next gets moved up ahead of some of these other operations, somebody might see an uninitialized node. Or if we have a situation where the write to P arrow next isn't atomic for some reason, which thankfully is not a real consideration on IA32 or x86-64, that will generally be atomic. Okay, so there's various things that we could run into, but the fact that we have a compiler that reorders instructions and a processor that reorders instructions basically means we're in trouble. This will eventually fail. Okay? Yeah, and you could also throw in other considerations, which we don't really talk about because we don't have a compilers class yet, but you can imagine also in the context of caching values in registers, if I did other things to P arrow next before, or I looked at it or something like that, before I went ahead and exited my function or something like that, I may have a register, I may perform that write to the register, and then later write that to P arrow next as a memory access. So, even caching stuff in registers can interfere sometimes with these operations. Okay, so these are the operations the writer thread performs, and we say they form a critical section because we need to make sure they all happen atomically. And if they're going to happen atomically, then we need to make sure that that thread has exclusive access to, well, probably at least P, the node that's pointed to by P, but we need to some way exclude other threads from looking at this state while we manipulate it. So that's kind of the challenge that we have here. So what's a really simple way of solving this problem? Okay, how do we avoid concurrency bugs? Well, you could get really clever and sophisticated and say, well, last time you talked about fences, and you could probably use a fence somewhere and actually force those operations to complete, and that would be a good choice. We'll actually talk about some of those things today. But if we were really naive and we use sort of the traditional sort of early approach to these kinds of problems, we would go ahead and add a lock. If you want to do anything to this list, you have to acquire the lock first. And notice that I said any thread on the slide. So if I want to read the list, I have to acquire the lock. If I want to change the list, I have to acquire the lock. And so we'd have to think carefully, is this thing actually accessed from interrupt context? And if it is, then I have to make sure I disable interrupts before I acquire the lock so that no interrupt handler can ever access it. And inside of an interrupt handler, it should be fine. It will have exclusive access because, again, you think, what can interrupt what? If I disable interrupts before I access this thing, then if I'm in the interrupt handler, I know nobody else is accessing it. Okay, so those are the kinds of fun things that you see when you implement operating systems. And I talk a little bit about multi-core systems. You can think about that as well, because remember, I may have other processors accessing this thing. If I do, then I probably need spin locks as well. So a few things like that. Okay, so the first question that you should ask yourself, and again, you may not be used to asking these kinds of questions yet, but you should get used to asking these questions really quickly because it'll, it's part of being a badass programmer. Why must readers also acquire the lock? They're just reading it. You know that they're not changing it. But given the way that we've designed this system so far, the only way that the readers will know that the writer is not writing is if they also acquire the lock. So this lock mechanism becomes a communication mechanism or a coordination mechanism between all the threads. The readers have to acquire the lock because the writer acquires the lock, and that's the only way that we can actually ensure mutual exclusion. Okay? So you can see that in a sense, the readers don't have to acquire the lock, but that doesn't mean our system is correct anymore. Right? So this is sort of, everybody cooperates by making sure they acquire the lock before they manipulate the shared data structure. And if they don't acquire the lock, we have a problem. Okay? So it's sort of voluntary collaboration here. Okay, so obvious issue with this approach. There's actually a couple of obvious issues with it. The first one is that readers should not block other readers because we know that readers don't destructively change the state. So why should readers actually change things? Okay, and remember the context is we expect this data structure is going to be read the vast majority of the time. We're not actually going to write to it most of the time. We manipulate it very infrequently. Okay. And it is okay if the writer holds exclusive access while it writes to this thing. Or at least we're saying that this is better than the old solution. But it's not great, and we'll talk about much better solutions to this as well. So we're saying that writers will accept it if they hold exclusive access to the list while they're modifying it. And so what we say is that this solution, as we have it here, a single lock guarding both reads and writes, making no distinction between readers and writers, has very high lock contention. Lock contention just means people spend more time waiting for the lock. I shouldn't say more time than. They spend a lot of time waiting for the lock. Okay, so that's what we mean when we say there's high lock contention. We have a lot of situations where threads are waiting to acquire the lock as opposed to doing real work. Yes?
Wait, what if you just check if the lock is taken?
Yeah, you could have a situation like that. If we had a lock where we could try to acquire it and we actually had other things we could go do, oh, I couldn't get the lock, I'll go do something else, then that would definitely reduce the lock contention, because you're spending a lot less time waiting for the lock. But if you have a situation where the thread must acquire the lock before it can do its next thing, which is usually the case, because usually we keep these kernel threads very simple in their sequence of operations. If it has to acquire the lock before it can do anything else, then you'll see the high lock contention again. And remember that we're expecting there to be a lot of reads, and so if we have a lot of reads, everybody's got to acquire the lock, and that's lame. Okay. So that is the concept of lock contention. So we'd like readers to not block readers, and we will accept for now that the writers will block everybody. But there's a simple mechanism for this. We actually mentioned it in passing last lecture. Does anybody know what we could use to allow readers to not block readers? Yeah, read-write lock. It's right in the name, right? You could be more fancy pants and say a shared exclusive lock and say, oh yeah, readers acquire the shared lock and writers acquire the exclusive lock. You could do that as well. It's the same thing. But now we can basically allow readers to overlap readers, but writers still acquire an exclusive lock. And obviously there's all kinds of considerations. We typically touch on some of these things in CS124 exams because we don't have time to talk about it in class. Yay. So, you have a lock where you allow multiple readers to acquire the lock at the same time. If a writer wants to acquire the lock and there is one or more reader, then the writer is not allowed to acquire the lock yet until they're all finished, and then the writer gets the lock. And you have, fairness issues. Should you allow people to hop lines? Things like that. You can definitely have readers get starved or writers get starved in certain circumstances unless you are really careful in how you design it. Okay, so we change to read-write lock, T, list lock. So we have something like that now. And there will be two lock request operations. We can still have only the one unlock operation because the lock can remember who is holding it right now. So you have either read lock, which means other people can also call read lock and get the lock granted, or we call write lock, and that will only be granted if nobody else is accessing it, and nobody else is allowed to receive a read lock or a write lock as long as I'm in my write lock. Okay? So this is kind of the approach. Pretty straightforward. And you can see that we're basically reducing lock contention. Readers don't have to wait nearly as long as they used to because now we allow multiple readers to overlap, especially since we know that we're going to have a lot of readers. And so you can see that, like I say here, we increase concurrency. So you can think of it, lock contention, the more lock contention you have, the less concurrency you have. The more concurrency you have, the less lock contention you have. Okay? So a few annoying issues. Readers still acquire a lock. You may not really realize that that's an issue. But you start to realize it when you try to build highly scalable systems where you have a lot of these kinds of locks. Okay? There's a little bit of overhead just accessing the lock. I say, I want to read lock this thing. Okay, that's fine. Give me your 100 or so clocks that you have to pay to acquire this lock. Okay? That's the minimum tax. Okay? So, and a write lock, same thing. So we basically still have an overhead for lock acquisition. And like I say here, the term is generally, this is usually described as lock overhead. So what is the overhead for acquiring the lock, for releasing the lock? Remember, when I release the lock, if somebody is blocked, on the lock, then I need to go wake them up. So then I have to move them from a blocked queue onto the ready queue. That takes a little bit of time as well. I'm touching memory, blah, blah, blah. So you can see that there's a little bit of overhead for this synchronization mechanism. It is not free. And writers still block everybody. Which, if you think about it, why do I lock the entire list if I'm doing something maybe only to the end of it? Or maybe I'm only doing something to this node. If I have, let's say, 45 nodes in my linked list, and I want to change one of them, or insert one of them, or replace one of them, why do I lock the entire list? So what might be an approach for solving that, to make it so that writers don't necessarily block everybody? What might we do? This is not rocket science. There's a pretty obvious answer. Yeah, I could do something like a read-write lock per node, some option like that. So what happens if I have a read-write lock per node? What happens to my lock contention? Does it go up or down? It should go down, right? The reason why is because each lock will guard less. Right now, we guard everything with one lock. But if each lock guards a lot less of the data structure, and that's what I'm coordinating access on, then I should actually see lock contention go down, unless I have some stupid situation where I only ever add stuff to the beginning, only ever remove stuff from the end, or some situation where the access pattern basically means that most of the time I don't actually require write locks throughout the list. So you could have access patterns that don't really play well. But in general, you should expect the lock contention to go down. We call that lock granularity. What is the size of the thing that I'm locking? If I decrease the size of the stuff that each lock is guarding, then I'm increasing my granularity. I need more locks. Now, what happens to lock overhead? It goes up a lot, especially if I had this approach where instead of having, if I have 45 nodes in my list and I want to traverse the list, now I have to acquire 45 read locks. That's pretty lame. Before I only acquired one. Okay, so you can see that, so this is what I just talked about. So we have more locks, each governing a smaller region of data. And it's interesting because you start having other challenges that start to emerge when you do this stuff. Because if I lock the node and I want to change its next pointer, well, do I need to lock the next node as well? What all do I need to lock to make sure that I do these updates correctly? So there's a lot of interesting new challenges that start to emerge. Let me see. Threads must acquire many more locks, so we talked about that. Writers can only lock the parts of the list they're changing, so we get reduced contention in the context of writes. I can read all the way up to where the writer is writing, and then I just wait for the writer to finish, and then I can continue reading the list after that. Okay, so I have something like this, a read-write lock in each node, and of course I actually still need one more read-write lock to govern the head pointer, because I could change the head pointer as well. So, like I said, there's a few other details here that we need to include, but we're not going to talk about them. All right, so anybody have any questions about this approach in general? Because what I'm going to do now is skip. This lecture has 60 slides. There's no way we're getting through it all if I don't skip a big chunk of it. The part that we're going to skip talks about a lot of little attendant details like I just mentioned. You start needing to do this mechanism called crabbing. You know how crabs sort of walk side to side? Well, the same thing when you have fine-grained locks in a data structure. You have to lock something, and then you own it. And if you want to do something to the next one, you have to lock it, and then you can release your current lock. So they call that crabbing, where you're sort of guarding each thing that you're stepping from as well as the thing that you're stepping to. You can read all about it. What we're going to do is start talking about the fact that this is kind of just a generally difficult approach. I'm not actually seeing any updates. Did my computer just lock up? Okay, here's what we do. I don't know why that was. Okay, so yeah, lock-based approach has a lot of issues. Okay, you have this big trade-off between how many locks do I have. The more locks I have, the more concurrency I frequently get, the less lock contention I have. But the higher lock overhead I pay. So the bigger the fee. Okay? If I have one lock or just a few locks, then I have a really low lock overhead, but I have really huge contention issues. No good, no bueno. So what do? Basically, locks have a lot of downsides. And so the real issue that we have here is we're trying to prevent different threads from seeing inconsistent state. That's really, so you take a step back. Our issue is not everybody must lock stuff before we manipulate shared state. The real issue is that we have this state that may be inconsistent. We just want to make sure people don't see inconsistent state. Okay? And like I say, the big issue with our specific example is that we can't really guarantee the order of these operations, how they'll be performed by one thread. Why do we care about that? Well, we really only care about it because multiple threads doing this concurrently may have interleavings that are invalid, where a thread is able to see incomplete state or inconsistent state because the other thread hasn't finished doing something but has become visible. Okay? So, like I say here, locks are helpful only in that they guard all the state changes so that we don't have to worry about ordering issues. That's why we like locks, right? Because I manipulate things and I guard my change so that nobody can see it until the manipulation is complete. So you have situations like that, okay? So what if we could actually impose a more intelligent ordering? And I hope you're starting to think, okay, fences, he's going to talk about fences. Well, it turns out that we actually don't need too much sophistication for doing this stuff. Okay, so T2 inserts a node. So first step, prepare the node. Okay? So, and I wanted to mention, I just finished, like at the end of last lecture, very hastily telling you that kernels don't really have allocators like, applications do. And then in this lecture, I'm using malloc and free. Frequently there's calloc, like kalloc, not calloc, and, or kmalloc, things like that for actually allocating memory in the kernel. We'll talk about how those allocators work in a few lectures, but we're just simplifying the presentation of the problem. So use your imagination. Those are kernel allocation calls if necessary and so forth. So we're just trying to illustrate the nature of the issue. Okay, so we prepare a new node. We don't insert it into the list yet. And you can see that new A, new B, new next, those things could happen in any order. We do not care. Okay? Obviously, the first operation should complete before any of the other ones do. If that doesn't happen, then you kind of have real issues. But we can presume that the last three operations can occur in any order because they're not visible yet. Okay? And you can see that T1, so T2 is the one manipulating the list. T1 can just go on. It doesn't care because it doesn't see the changes. They're not even visible. If it follows next, it doesn't see the new node because it isn't actually in the linked list yet. So then step 2 is that we want to atomically change P arrow next to be new from being what it was before. And when we say atomically, we mean so that T1 sees it either as the old value or as the new value, obviously not some amalgam, because that would also be horrible. Okay? And like I say here, if the CPU can perform that single word write atomically, then threads fall into camps now. They either see the old version of the linked list or they see the new version of the linked list. They can't see some weird mangled version. Okay? So we do this. That has to be a single atomic operation. And so the result is that readers never see an invalid state of the list. Okay, so that's all like, okay, that seems simple, but we could do this with fences. Who cares? What's the big deal? Why are we making such a big deal out of this? Well, it turns out it's a little bit more complicated than this. So the mechanism, as fully developed, and we're going to go through most of the general nuances of it today. So it's called read, copy, update, and you've probably heard of it. Who's heard of RCU before this lecture? Before this class? Okay, wow, this is really cool because this is actually becoming one of the more common synchronization mechanisms within Linux and is becoming more and more widely used. So it is the wave of the future, the wave of the present, and it basically is a lock-free approach to managing shared state. You may have heard of this term as well, lock-free. What we mean is let's orchestrate our operations between multiple concurrently executing threads in such a way that we don't ever need to acquire locks. I tell you, it's way faster, and it's way more scalable with the number of CPUs. I have some charts I'll show you toward the end, where lock-free approaches are actually really powerful in achieving very high concurrency without hardly any lock overhead. Okay, so all changes to shared data structures made in such a way that the concurrent readers never see the intermediate state. They only see either the old version or the new version. And remember, I said there's an atomic change, and so you can divide people into two categories. You either see the old version or you see the new version. And the changes are broken into two phases. This is where the term read, copy, update comes from, because you have readers, and then you, if you want to write, then you do a copy and then an update. Okay, so you make a copy of the specific parts of the data structure that will be the new version, and you can do whatever you want in whatever state you want, in whatever order you want. Who cares? Okay, so that's the copy part. And then once you have perfectly crystallized, ready state to expose to the rest of the world, then you do a single atomic operation. That's your update. And that exposes the changes to other readers. Okay. And virtually always in read, copy, update, and also I should say in a lot of other lock-free data structures, I should say, because you can also have atomic data types where you're not manipulating a pointer. But generally in lock-free data structures and in read, copy, update in particular, this atomic operation is always changing a pointer. Okay? It's pointing from one valid version of the shared state to another valid version of the shared state. And since it's atomic, again, people either see the old version or the new version, but they don't see something gross. The way that it's generally described is that this change is a publication of the new version of the value. So, like I say here, it generally is described as publish subscribe. So we prepare something for publication just like you would at a newspaper or a magazine. I know people are like, what are those things? Pretty soon that's going to be the way to, oh, it's just on the internet. So, but anyway, once you have it all prepared, then you publish it by changing the pointer. And so you have to make sure that all the initialization is completed. And that's really easy to do. We just enforce a memory barrier. Okay? And since it hasn't been published yet, we can get away with just using a write memory barrier. Okay? And like I say here, of course, you need to make sure the compiler imposes an optimization barrier. That's really easy. Remember, that was like no assembly code. We just tell the compiler to stop pretending that that value is cached anywhere. Okay, so we can implement it like this. Oh, and it looks like I need to work on my font, so I apologize for that. Atomically publish a value v to pointer p. Okay? So we have this magical function, which is actually a macro called RCU assign pointer, which atomically assigns v to p. And so you can see we have a write memory barrier if we're on a multiprocessing system. If we don't have if we don't have a multiprocessing system, that thing turns into nothing, and we just perform the operation. Okay. And the reason why is because IA32 and x86-64 really love programmers. As long as these operations are word-aligned, it's already atomic, even in multiprocessor systems. So we don't actually have to worry about doing anything extra. We just perform the write, and that thing is automatically going to be atomic. Go us, that's simple. So this is the way that T2 would now update the linked list. Notice we do all of our stuff. That's the initialization, setup, blah, blah, blah. And then we call RCU assign pointer. That publishes the new node. And it turns into that code up there, which, you know, is really cheap, right? So what is our locking overhead? Well, I mean, it's not really locking anymore. So what's our overhead of RCU? Well, it's really cheap so far. Okay. So that's publishing. Now, T1 needs to see whatever the current state is. Now, do we care what the current state is? Not really, and you'll notice that this doesn't have necessarily the same consistency guarantees as databases do. We'll talk about that toward the end. But T1 just needs to see whatever the current state of the pointer is, and again, it needs to do that atomically, so it needs to either see the old value or the new value, and it shouldn't see anything intermediate. So this is what we had. We had T1 looking for a node with a specific value of A. So we get the head pointer, We start with b being -1 because let's say we're retrieving b out of the node with a specific a, and we say if p arrow a is the value, then we pull out the b and break out of our loop. Otherwise, we go to the next node. Okay, so where do we care about? Well, we care about list node star p equals head. That needs to get a value that may be manipulated through RCU. And p equals p arrow next is a value that may also be manipulated via this read, copy, update mechanism. So we say that T1 is subscribing to the value of the pointer. Okay, publish, subscribe. So pointers change, we say it's a publication. Somebody reads the pointer value, it's a subscription. Okay. So we need to make sure that p arrow next is read before anything else happens. This sounds crazy, right? Seriously, you want to read p arrow next before any accesses to p arrow a or p arrow b. So we're saying that that p equals p arrow next needs to finish before the rest of the loop that comes after it in execution, right? Well, the reason why we need to care about this is because there are a few processors, cough, dec, alpha, cough, where this can actually happen. It will actually schedule the p arrow a or the p arrow b to occur before p is updated to point to the node it's supposed to point to. Okay? Now, is that actually what happens in reality? No, the real issue is that you have these two data caches in the dec alpha processor that are not kept coordinated with each other. And so you could have the old value of p read from 1 to handle the A access or the B access, and the new value of p is in the other data cache, and they aren't coordinated. Okay, that's the real way that it happens. But in this situation, IA32 already ensures that reads occur in a reasonable order. So p equals p arrow next will always happen before we get to the next iteration of the loop and read out p arrow A and p arrow B. Okay, so thankfully this isn't a no. Yes, question? Yes, so the issue here is you can't really release things until you've coordinated with everyone else. You're jumping ahead of the story. This is good because you're thinking about the implications of what we're talking about. But yeah, we'll actually address that issue. It is surprisingly complex. So we'll definitely address that. Yeah. Okay, so this is probably not worth mentioning, except that you do need to think about it on processors other than IA32. IA32 is, like I said, really nice to programmers, at least when it comes to concurrency. Okay, so we encapsulate subscribe in a macro. Okay. Again, what do we mean by subscribe? I'm reading the value of a pointer. Okay, well, like I say here, we call it RCU dereference. Again, you have SMP read barrier depends, which if you're not on a multiprocessing machine, or a multi-core machine is really how I should say it, then that turns into nothing. If you're on a machine where reads are ordered all the time, then it turns into nothing. If you're on a dec alpha, then it turns into a read fence. Okay? Because you have to make sure that the reads finish before this read occurs. Okay? So what do? Type of p underscore value equals access once. What does that mean? Okay. Access once is a macro that ensures that you actually read it. Like the compiler can't just trust that the value's in a register. It has to read it from memory. Okay? I don't think I have a definition here of access once. Yeah. So the definition of access once is cast it into a volatile version of the same type and then read it. When you cast it into a volatile version, you're telling the compiler, this thing may change, and I don't know who might change it, but it may change, so you better read it. Okay? So access once emits no additional instructions. It just makes sure that we read it from memory as opposed to reading it from a register. So it may be slightly slower, but it's not significantly costlier. And then we just return the value that we read. Okay? That's all we do. Okay? So subscribing is cheap, and publishing is cheap. This is really looking nice. This is looking like a fantastic approach. Okay? So this is the updated version of our T1 code. We RCU dereference the head because, hey, we're subscribing to it. And then p equals RCU dereference p arrow next. And that's how we get to the next node. Okay? So far, this is looking pretty cool. Okay. Yeah, like I said, the cost is shifted onto the writers because they may have to do extra stuff. Because instead of just changing things in place, that's obviously the cheapest way of doing it. Instead of just creating it in place, now I have to make a copy and mutate the copy and then publish the copy, and then clearly I have some garbage that I have to clean up. So the writer has to do extra work, but we're presuming that this writing is going to happen very infrequently. And writers aren't blocking anybody anymore. They can go ahead and do things on the side all by themselves. Okay? Now again, the observant student will be asking the question, well, yeah, but there's also another issue of what if two writers are trying to write to the same thing? Let's say we have two writers trying to write to the very same node at the same time. They both create copies. They both want to publish. Now you lose a node. Well, that's a very good question. We won't talk about how to deal with that. I wish I could tell you all about lock-free data structures. Mike and I actually were kicking around the idea. There's this book, 7 Concurrency Models in 7 Weeks, which I love. It's a great book. The person is clearly more in the functional programming vein, which there's nothing wrong with that, but it constrains what kinds of concurrency models that they look at. And Mike and I have talked longingly about having a CS11 concurrency track or teaching a class on different concurrency models and taking people through all the different approaches because there's some really clever stuff, and you guys should know it, but that probably won't happen anytime soon. So we dream. Okay, so yeah, readers incur 0 overhead. Writers incur low overhead. Now, like I said, writing occurs infrequently, but it still costs more than it did before. Okay? So we're sort of expecting that we've basically thrown away all the lock contention, or not lock contention, we've thrown away all the lock overhead of acquiring and releasing locks. We're actually losing all of our lock contention as well. Presumably, that is a much larger benefit than the new cost that we're now incurring on writes, taking more effort. Okay? So that's the idea. That's the premise, is that this is actually going to be overall much less costly. It turns out in practice it totally is. But even though writers are more expensive, it's I should say the specific modification of state is more expensive. The savings overall is incredibly huge. Okay, so we want to modify a list node. So you see now P is pointing at the second node. And we've used RCUT reference to navigate to P and so forth. We can't change it in place. We have to make a copy. So notice we allocate a new node. We set what A and B should be. And we go ahead and, so what are we doing here? We're saying that B is set to 15. So yeah, we have to create a new version where, I think this is actually a bug in my slide because the new node doesn't actually have B as 15. Our kernel is buggy now, so I'll have to make sure to update that. But you can see that this is the idea. I want to modify a node, then I have to create a copy and change the value, which I failed to do, and then use RCU assigned pointer to do that. Okay. And so, like I said before, this means that readers basically fall into one of two categories. Either they saw the old value of prev arrow next, and they saw the old version of the node, or they see the new value of p arrow next, and now they see the new version of the node. Okay? Not on my slide because they're the same, but in concept, that's what they would be seeing. So the upshot is that all readers see a valid version of the state. So we don't have inconsistent state anymore, but we do have the fact that some readers might see an old version and some readers might see a new version. If we're insensitive to that kind of issue, then we're fine. Okay, so are we finished? And this is where we start talking about releasing resources. I created a new copy, changed its values, published it, and now I have the old version. P is pointing to the old version, right? So I need to add in some operation to release that memory, or else my kernel will quickly crash because I'll run out of space, right? So I have a free P. What's the issue with this? Yeah, there might be a lot of readers, in fact. You know, you could have situations where you might have quite a few readers. If you look for one node and then you need to change something 15 nodes down, and so you go to it and you start to change it and you want to do things like that, you might have a lot of readers that are actually affected by it. So the obvious issue is that if somebody's following the old version of prev arrow next, they may be using the old node when the free is called. So really all the complexity of read, copy, update centers around this issue. When can I free stuff? That's really what all the complexity of read, copy, update comes from. Okay, so we have to make sure that the data is only freed after all the people who were observing it have finished with it. And so how do we actually tell now that readers have finished what they were doing? That's the big question when it comes to read, copy, update. Because remember, we don't really have very much that we're doing to synchronize access to these data structures. People are sort of doing their publish subscribe thing, but that's it. They haven't really said, hey, I'm in this node, because we don't like having to do that. So we have a new sort of semantic rule that we apply. And we define it in this term, a read side critical section. What we basically say is that when we start reading this data structure, or I subscribe to some value, I enter what we call a read side critical section. Okay? When I'm finished using that pointer, I leave the read side critical section. And there is, okay, so we haven't gotten to the rule yet, but this is how we denote them. We have RCU read lock. Okay, do we actually have a lock? No, you'll see how easy this is to implement. RCU read unlock, and we end the read side critical section. Okay, so this sort of denotes the space that we're actually in the read side critical section. So since our thread is just traversing the list looking for a particular node, we go ahead and just surround the entire thing in a read side critical section. I read P, I go ahead and look at P, and I continue to look at P, and then I get P arrow next, so why don't I just throw the entire thing into a read side critical section? If I had situations where I finished using P, maybe I pull out P arrow next or something like that, I suppose you could break this into multiple read side critical sections, but in this case, I kind of can't. I have to have the whole thing in a single read side critical section. Okay? Here's the rule. It really is this simple. It's funny because instead of using locks, we're training programmers, which is arguably more complicated. But this is why it's such a complex concept, is because you have to get programmers to think differently about concurrency. So the constraint on read side critical sections is that you are not going to ever allow readers to block or sleep inside of that read side critical section. That's the rule. Okay? So internalize that fact. It turns out that people have come up with other versions of RCU that relax this constraint, but the original RCU implementation said if you're subscribing to pointers, you're not allowed to block, you're not allowed to sleep, which means you're not allowed to be preempted. That's kind of really important detail as well. Okay? So I'm inside a read side critical section. I have to be able to progress until I finish. Now I can be blocked. Now I can block. Now I can do whatever. Somebody can put me to sleep. Okay? T1 follows this constraint. It makes no system calls. It doesn't it doesn't acquire any locks. We could try lock if we wanted to, but we can't lock with a blocking lock call. Okay? So you can see in here, we're going to progress until we're finished and we leave the read side critical section. Okay? Yes? Well, so what if a timer interrupt comes in? We're not allowed to interrupt this code. So that kind of indicates what we might do inside of RCU read lock. Maybe we have to disable interrupts. And inside RCU read unlock, we re-enable interrupts. We're not allowed to be preempted. That's the rule of RCU. So RCU read lock makes sure that we cannot be preempted. This is not inside user code. This is inside kernel code. Yeah. We're not, we haven't even started talking about user land yet. We're still inside the kernel. So yes, we're allowed to do this. We disable interrupts, we do our thing so nobody's allowed to preempt us, and then we unlock at the end. Okay? All right, so yes, we use read side critical sections to define when old data may be reclaimed, because if you think about it, we have all these readers doing their magic, accessing data structures, playing along, not stepping on each other because they're just reading. And you can see that each reader's arrow starts with a call to RCU read lock, and the arrow ends where they call RCU read unlock. So this is their extent. Yes?
So doing this, you'll almost never have interrupts on.
Doing this, you almost never have interrupts on. Well, that's not actually true because there's other ways to prevent preemption. So we'll talk about that in a second. The other thing, too, is that you really only have this issue if the interrupt handler also wants to manipulate the shared data structure. If the interrupt handler is doing something completely unrelated, you can let it preempt, and that's perfectly fine. As long as it doesn't kick that reader away from completing their read side critical section. Because remember, interrupts have to execute till completion. That's fine. They do it. They return back to the code that was interrupted. The reader continues until completion, and then the reader can be preempted. So really, not having interrupts is only about if we have the same shared data structure, the interrupt handler can dispatch away from that kernel thread. Okay? And so we just make sure that that's not allowed. Okay? We'll talk about that briefly because we don't have a lot of time. Okay, so we have RCU assign pointer. That's where we replace the old version. And so you can see here that we have readers now in two groups. Where does the group start? Well, if RCU assign pointer is on the right of the start of the arrow, then I'm in the old group. And if it's on the left of the start of my arrow, then I'm in the new group. Okay? And since it's atomic, no reader's arrow is allowed to start on that line. They either have to start before or they have to start after. They're not allowed to start on the line. Okay? So what readers might see the old version, I'll just go ahead and throw this up here. So RCU read lock falls before the writer calls RCU assign pointer. When can the writer reclaim the old version of the data? Just looking at the picture conceptually, when can the writer reclaim the old version of the data? If your arrow starts before the line, you look at whose arrow is the longest. When that arrow ends, that's when you're allowed to reclaim the data. Does that make sense? Okay. So when all the readers who saw the old version have called read or RCU read unlock, then you know that you can go ahead and reclaim the data. Okay. So we call this, yeah, and so this is the earliest. We can reclaim it even later. That's perfectly fine. It won't be perfect resource management, but we could even wait longer if we wanted to. But we can't go any sooner than that line. Okay. So we call that the grace period. The period where we're letting readers get their act together and get out of the data structure. Okay? Now, it's not really like they better hurry up and do it. The writer has to wait until the readers are done. Okay? So the writer has to figure out when that grace period is over. And it doesn't have to be precise, but it does have to be accurate. It can't be shorter, sooner than the grace period must end, or can end, but it can be longer if it wants to. So again, we have this operation, synchronize RCU, which encapsulate this. And so the writer does something like this. Okay, we allocate our thing, we publish the pointer with RCU assign pointer, and then we call synchronize RCU because we need to free stuff. After synchronize RCU returns, okay, so synchronize RCU blocks until all the readers are finished, then we free the old thing. Okay, so we go ahead and replace or add synchronize RCU to our diagram. Okay, so how does this actually work? This is the interesting part of read, copy, update. Readers are not allowed to sleep or block. Okay, they must progress until they call RCU, unlock. Okay, to end their read site critical section. So here's a question. How many readers are allowed to be executing at any given time? If I switch away from a reader and it gets preempted, it can't be inside of its read site critical section. I'm not allowed to do that, right? Just one. Is that how many CPUs are on the system? What if I have 4 CPUs? How many readers can be active? Yeah, 4. So basically, I can only have the number of readers. I should say the maximum number of readers is the number of CPUs on my system, right? Otherwise, if there was one more than that, then I would have had to context switch away from it and it would be blocked. So that's not allowed. That's the constraint. We're not allowed to switch away from a reader until it finishes its read side critical section. Like I say here, if the reader's inside its read side critical section, it has to occupy a CPU. Okay, so we also, like I say, require the OS can't preempt a kernel thread that's inside of a read side critical section. Okay. So basically, we disable kernel preemption in these contexts. That's just basically what we were saying before. Now, what does this really mean? We already talked about preemptible kernels versus non-preemptible kernels. Not being able to preempt is not the end of the world for multitasking. Hopefully you all remember this. Hopefully you guys got that. All we do is basically fall back on scheduled context switches. We finish the read side critical section, and then we context switch after we end it. Okay? It's not like it's the end of the world. We just can't context switch right now. Okay? So the CPU executes a context switch. Then we know the kernel thread must be outside of its read side critical section, which means it's ended. Okay? So we can actually exploit this. We just have to make sure that there's at least one context switch per CPU, and then we know we're done. Okay? And like I say, that may not be a perfect bound, but it is an upper bound that includes the grace period. And so that's what we do. Which is weird, but we just watch to make sure that everybody has done at least one context switch, and then we're finished. Okay? This is the simple, naive approach. Synchronize RCU. Well, I'm going to enumerate all the CPUs in the system. I'm going to switch my writer thread to each one of those CPUs in sequence. And then I know synchronize RCU is complete. Okay? Where run-on might simply say, I'd like to set my processor affinity to whatever CPU's value is, and then I yield. And the next time I wake up, I'll be on that processor. And then I set it to be the next processor, and then I yield. And then I wake up on that processor. So synchronized RCU is just hopping from core to core. And once it's made its trip through all the cores, then it knows that there's been a context switch on every core. Now, are there faster ways of doing this? Definitely. Real RCU implementations don't do this, but it's nice to know that there's a really simple implementation that can actually do this. Okay. And of course, once you have a context switch on each processor, you know that you are out of all the read side critical sections of the readers that started before synchronized RCU was called. Or actually, it's the publish, the RCU assigned pointer. Okay. So, single processor system. If I'm in a writer, all the read side critical sections that came before I write are done. Because if they weren't, then I would not be running right now. Okay? So synchronized RCU turns into a no-op, which is crazy. Okay? Okay, so we're not going to spend very much time talking about that. If I'm on a multi-core system, then it's a little bit more complicated, but like I said, there's definitely been optimizations to that approach, so we won't talk about that. You can read about it. Read lock and read unlock, also simple. Synchronized CPU uses context switches. Okay? So they don't actually have to do any bookkeeping. If you're on a multi-core system with kernel preemption, this is what I was saying before. You're inside of a kernel thread. You need to make sure it can't be preempted inside that read side critical section. So you just disable preemption. You fall back on scheduled context switches. It's not the end of the world. Okay? So preempt disable, this would be like the Linuxy version, would just up the preempt count so that it can't be preempted. And then preempt enable would just decrement the preempt count. Okay? So yeah, single processor system with an OS that doesn't allow kernel preemption. Read lock and read unlock don't do anything because preemption's already not possible. Okay, again, kernel preemption. We still have multitasking. So read lock and read unlock become super simple. So I actually show you a single slide in a second. Let me go ahead and just dive through this last part. RCU is awesome, but it is just as much about training programmers to think differently as it is about coming up with a technical solution. Because you'll notice, okay, I've got to wrap stuff here. The real key is readers aren't allowed to block. That's the key there. And then all this other magic actually works. So like I said, there's as much about training programmers as there is about actual synchronization. Okay, like I say, no lock, so you have basically no lock overhead. The implementation, at least a naive implementation, is super simple. And most of the time, especially on a good processor like the Intel processor, super fast. This is the entire implementation. Okay, and this has support for kernel preemption and multi-core. Crazy, right? If you're doing this for a single core operating system without kernel preemption, then read lock and read unlock become nothing. Synchronized RCU becomes nothing. And obviously all the SMP operations drop out. And you have your entire RCU implementation. Okay? It's basically no code. And it's all about training people, really. So it is only useful in specific circumstances. Like I say, there are many more readers than writers. Consistency, like in terms of database consistency, must not be a strong requirement, or else you're going to be sad, because you can definitely have threads seeing old and new state in ways that are not very well defined. And so if you don't have these constraints, then RCU isn't your solution. Okay, but thankfully, there's a lot of parts of, it's probably scary, but there's a lot of parts of operating systems that don't actually have strong conditions here. Okay, let me show you really quickly, and then I'll let you go. RCU use in Linux, skyrocketing. The kernel is using it more and more and more, and it's getting faster and faster and faster. This is the other one that I really like to show, where up and to the right is not always good in computer science. It's really good in business. But in this case, you can see RCU versus read-write lock overhead as the number of CPUs increases. And so you can see how much read-write locks slow down as you increase the number of CPUs, and the coordination costs go up. RCU basically remains flat. Okay, really great. Now the rest of this stuff, this talks about various versions of RCU that suck less, and you start getting some really powerful mechanisms because you can support both blocking and preemption in some of the more advanced versions. And Paul McKenney is basically the guru on read copy update, because he kind of invented it and talks a lot about it. So he has a lot of details about it. And you can read. Oh, and there's even user versions if you want to actually do this in user space, which is crazy. Okay? So any questions? All right, I hope you enjoyed that. Next time we'll talk about something that's actually necessary, but this is really cool. And so I wanted to make sure you guys saw it. So I'll see you all next time. I'm not sure if this would have been a better lecture to include earlier, since you guys are having to actually implement schedulers already. But I mean, you can let me know in the feedback comments on the project if you think this lecture should have been earlier, and the next lecture too, although the next one is kind of more esoteric schedulers, so you don't have to implement anything from that lecture on the assignment. So we're going to sort of start talking about process scheduling, because of course the operating system is responsible for making sure all the applications can share the hardware. We talk about that quite a bit earlier on in the class, but the most important hardware resource, and you could say the most limited, because there are very few of them compared to everything else, would be the CPUs. And so the operating system has to make sure that everybody can have a fair share of them, depending on what they're doing, to satisfy various criteria. Sometimes unfair is fine. So yeah, while some processes are waiting for I/O, we want to make sure that the other processes in the system are able to use the CPU, because clearly if somebody's waiting on I/O, they don't need the processor. So we can remember that we categorize processes based on their state, and really we only care about two states for the next few lectures, and maybe blocked peripherally, but we really only care about running, so who's on the CPU, and we care about ready, who could run if they had a CPU, but they don't currently have a CPU. So those are the two process categories we really care about right now. And so the question of scheduling is, how do we figure out who should get the CPU, who should get bumped off the CPU, those kinds of questions. These are really what scheduling is all about. And thankfully, this is a subset of all processes. The ones that are blocked, we don't even have to think about. They get to just sit there and continue to be blocked. Now remember that there's multiple schedulers. We have the long-term scheduler, which governs entry of processes, so this would especially be relevant in a batch processing system. I have 30 processes, or I should say 30 programs all queued up and ready to load, ready to unleash, and the long-term scheduler determines how many should I release, which ones should I release so that I can achieve a good I/O mix, so that I have good utilization of CPUs and good utilization of peripherals. Medium-term scheduler can fine-tune the process mix to make sure that if some processes, I have too many CPU-heavy processes, I will suspend some of them so that there's less pressure on that. We can utilize more peripherals and so forth. But we really don't talk about the long-term and medium-term schedulers anymore. Okay? Now we really focus on the short-term scheduler because that's basically the way that we use computers now. So we're going to, most of our discussion will be on the short-term scheduler. And so I want you to keep that in mind as we're going through things. The other thing is that we're scheduling kernel threads. So remember that a process corresponds to a kernel thread. The kernel thread is kind of the tip of the iceberg into the kernel, and the kernel works with kernel threads. And of course, the user process's behavior affects what the scheduler sees as far as the kernel thread's behavior. We are able to distinguish whether we're executing code in user space or in kernel space. I should say user mode versus kernel mode. The two terms are so similar to each other, user space and kernel. User space and user mode, that it's, you can think of them as being roughly equivalent in this context. Okay, so yeah, the scheduler is going to be working with kernel threads because we've already switched away from the user space program at that point when we're scheduling. Okay, now typically we have a function called schedule or something like that that actually handles scheduling. I say that scheduling and context switching is always performed at a single point in the operating system kernel. This is just to keep it simple. When you have things like kernel preemption, even then you try to set up so that you can enter schedule and have things look reasonable. And again, if you looked at the 7th assignment in CS124, you probably saw that we do a similar thing, except we no longer can do this on a the cooperative basis. Now we do it on a preemptive basis where we interrupt the user process, we make it look like it called schedule, even though it didn't. We basically update the stack and everything so it looks like it called schedule, and then off we go. So we can do similar things in kernel space, and so we still end up with a single point being where scheduling occurs. So kernel threads, yes, they see themselves entering schedule, they see themselves returning from schedule. Schedule's written in C, so if you're on a Unix-based system, then CDECL rules the day. Now I imagine on Windows you're using standard call or something like that even inside the kernel. Okay, so, but what's interesting about the schedule function is kernel threads, they see themselves calling it, they see themselves returning from it, but we have no idea what happened in between, right? I call it, and then somebody else returns from it, and I don't know it because I'm not running anymore. And then later, eventually, somebody calls it, and it returns as me. So processes, each kernel thread sees itself entering and exiting schedule, but what's usually happening is that we return on a different thread than we start. Now, why would we return on the same kernel thread? Well, if it's the highest priority thread right now, if there are no other kernel threads to schedule, those are the kinds of situations where we might come back on the same kernel thread that we entered on. Now, there's two tasks that need to be performed. One is obvious from the name. It's figuring out who should go next. But the other thing that has to happen is switching from the one kernel thread to the next. And that is a very important detail. So we are going to spend a little bit of time talking about it. Not a lot. Thankfully, this is mostly handled for you in Pintos. And you already got to see enough of this in CS124 that we don't need to beat you over the head with it. But that second part, switching from one kernel thread to another, is typically called dispatching. And it's handled by the dispatcher. The dispatcher is responsible for restoring the new kernel thread's CPU context. Okay? And so like I say, if the new kernel thread has a user process or user thread associated with it, then we need to go ahead and restore the user configuration so that it looks like the process should when we get back to the process's execution. Okay? So we want the dispatcher to execute as quickly as possible. We are not allowed to waste cycles here because this is an unavoidable step and it is only overhead. So we don't do any thinking, we only do. Maybe, if we're definitely switching to a different process, then we have to update the memory management unit. So we have to change the page table. We have to flush the translation look-aside buffers. If we are staying within the process, just switching to another thread, or we're going back to the same process that called in, then we don't have to update the MMU, so we skip those steps. We always have to update register state, those kinds of things. We have to make sure that we do those things when we dispatch. So what can we do? We just try to make that as fast as possible. Now, an unusual detail that I thought was worth mentioning in class was that switching between kernel threads actually involves 3 threads, not 2. You think, okay, I'm switching from A to B. Okay, well, where's this 3rd thread come from? And you notice it immediately when you look at the dispatch code from Pintos or from any operating system where you can look at the source code. You see switch threads, you have current and next, and then we return a thread star as well. Why would that be? Okay. And so you have to look at this, and again, when you look at these kinds of things from the standard application programming perspective, you say, this makes no sense. This is why I don't want to program kernels for a living. I want to stay in user space because it's much safer. Okay, but we return a thread star because you have to think about what does the thread coming in see and what does the thread leaving see? Because remember, we have a certain machine context when we enter this function, and then when we leave, we're in a different machine context. So what does that other machine context have for switch threads? So notice I switch from thread A to thread B, so I call switch threads A, B. This is not necessarily exactly how the code would look, but we're just illustrating. And so the function switches from thread A's context to thread B's context, which means the stack changes, the registers change, and so forth. Now we're switching from one kernel stack to another kernel stack. We're still in kernel mode. So when thread B resumes running, we're still inside switch threads, but what arguments does thread B see on switch threads? Yeah. Yeah, that's exactly right. When B resumes running, it's going to see itself as the current thread, and whatever guy the scheduler said to switch to next is going to be what B sees. So what happened to thread A? That's the issue. Because what if we're switching to thread B because kernel thread A is ready to terminate? We need to clean up. Or other issues like that. We need to make sure that what if we are switching away from thread A because it's now blocked and we need to put it into the appropriate blocked queue? So we can't lose thread A in this dispatching process. That's why we return a thread star. Okay. So yeah, like I say here on the slide, it was switching away from thread B to some other thread C, so we'd see switch thread B and then something else. We don't know what. Perhaps A, but we have no idea. And so it's, if you just relied on the arguments, you lose the thread that you're switching away from because the machine context no longer holds it. It's whatever it was on B when we switched away from B. Okay, does everybody understand that? Hopefully, it's a pretty straightforward thing when you see it. But every time I present this, every year that we teach this class, people are like, I don't know. Oh, I see now, because we're actually changing machine contexts in this function. Okay, so this is the thread switch function. So basically, we need to make sure that we don't lose the current thread, or I should say the old thread that we're switching away from. So because of the reasons that I stated before, we may have cleanup operations we need to do because the thread's terminating. We may need to put it into blocked queue, some other thing. We have to make sure that we don't lose those things. So what switch threads does, there's a little bit of setup code to make sure that the thread that comes in, the current thread, is going to be returned to the caller, even though we're switching contexts. So if you look at the Pintos implementation, what it does is it squirrels away current into EAX, and then it goes ahead and does the machine context switch. So that even though current and next change, we switch from A to B, and then suddenly after the switch, it's B and somebody else, EAX still holds A, and that gets returned, because remember, with CDECL, EAX is the return value, and then that way we can still get to the old thread when we return. Okay, any questions? Now, is that really critical to anything you have to do in Pintos? Not really, but if you actually follow the advice of the assignment and walk through a context switch, then you may have come across this code, and that's the reason why we have to have 3 threads instead of just 2 when we do a context switch. All right, so now you know. Okay, so getting back to scheduling, there's a lot of different ways we could evaluate scheduling algorithms. So I say measures to evaluate scheduling algorithms with. So we could look at how busy do we keep the CPU. That's one thing we could do. We could say how many processes do we finish in a certain amount of time. That could be another measure. Turnaround time, how long does it take to finish a particular process? You know, we could either take a specific process or a specific kind of process that we want to finish quickly, or we could say, on average, what's the turnaround time of the scheduler? How much time does a process spend in the ready queue? I.e., it could run, but it's not getting to, so it's frustrated. If it had the CPU, it could feel frustration, but it doesn't, so it just sits there. And then response time. How quickly does the process begin producing output? Sometimes you see that as a goal, but not always. So you can imagine that of all of these various measures, we could try to optimize for any number of them. Maybe just one, maybe a bunch. So scheduling algorithms, there's many different scheduling algorithms that you could look at. And a lot of times when you see scheduling algorithms and operating systems, they are in the family of the scheduling algorithm we talk about, but then they have various tweaks that are hopefully going to improve various things that the operating system is trying to achieve. Okay, so processes themselves. Processes tend to have times of computation, periods of computation, followed by periods of I/O, and then periods of computation, and then periods of I/O. Compilers are a great example of this. I load a file, I parse it, okay, I need to load this other file, so more I/O, and then I parse it, and so forth. And then I start generating, abstract syntax trees, and I try to, do high-level optimizations, blah, blah, blah. Now I'm in memory. I'm, using the CPU, and then I write intermediate results out to disk. Well, that's going to be another I/O burst. So you can see that processes tend to do a bunch of computations and then a bunch of I/O. And there's a significant amount of research about this. It's kind of interesting because how you get these measures is interesting as well. You can imagine if you have an operating system kernel, then you can instrument the kernel to figure out what are these behaviors. So that's kind of a fun thing to explore. That would be a great little project to try to reproduce some of these measurements. But anyway, like I say here, the research usually characterizes the distribution of CPU burst lengths as being exponential. So you have a lot of really short ones, and then it falls off. You have relatively few that are actually long CPU bursts. We have schedulers that are cooperative, which basically means that they don't schedule very much. They basically only decide who should run next when the current process kindly releases the CPU. Okay? So again, this was how early Windows behaved. This is how early Apple operating systems behaved, and it's a pretty simple thing. A lot of simpler operating systems have this approach. I got to work on a computer system that unfortunately is no longer available here when I was an undergrad, and it had a very simple operating system with a cooperative scheduler, so you had to behave or else the system would lock up. But then you have schedulers that are more aggressive and will actually preempt the current running process if it spends too much time on the CPU. Okay, so most of our schedulers now are preemptive because they just are more, they're more robust in the context of programs with bugs, which it turns out happens from time to time. Okay, so simplest algorithm, first come, first served. Why do we even talk about this? Well, really, just because we want to set up where round-robin scheduling comes into the picture, so it's not very interesting. But basically, the ready queue is just a FIFO. Whatever goes in first comes out first, and it gets the CPU as long as it wants it. When it's done, when it does something that causes it to block, or it yields, or it terminates, those are sort of the 3 events that we care about, blocking, yielding, or terminating. Then it gets off the CPU, and the next guy that's at the front of the FIFO gets the CPU. And obviously, if it blocks or yields, it goes into the appropriate blocked queue, and then enters the back of the FIFO, and then walks all the way up to the front again. Okay. So first come, first serve, not preemptive, not very exciting, but it is a really simple scheduler to implement if you don't want to have to think very hard. And again, writing an operating system is complicated enough, so you can always start with first come, first serve, and then make it more intelligent later. Okay? And it turns out that this actually does pretty well a lot of the time because most programs eventually do an I/O burst, and so they get blocked and they get out of the CPU and let somebody else run. So like I say here, it's good for batch processing because typically you don't have a lot of interaction and you just want CPU tasks to complete as quickly as possible. It's bad when you have programs that don't terminate, which is not a surprise. And if you need responsiveness, first come, first serve is terrible because we have no preemption, which we really would need for good interactivity. Now, if we add preemption based solely on time slices, then we get round-robin scheduling. Okay? So now we're saying you can have as much time as you want as long as it's less than this amount, and then you get booted off the CPU, and somebody else gets to run. So the ready queue is still a FIFO, and again, we have block, yield, or terminate, but then we have another criterion, which is you used up your entire time slice, and then you get booted off the processor as well. So this is now a preemptive scheduler, just by adding this little facility. And if it gets preempted, then it goes back to the end of the FIFO. If it yields, it goes back to the end of the FIFO. If it blocks, then obviously we all understand what happens there. And we have a really interesting knob, which is this time slice size. What do we do with that? Well, if you give them everybody a large time slice, then batch processes love it because they're going to get a large amount of time uninterrupted. And obviously, if you had a whole bunch of CPU-intensive tasks, you'd get very few context switches. Remember, context switches are overhead, so the less we do that, the more CPU time we have for computing. Then, so that's nice, but it's terrible for responsiveness because you have to wait for all the CPU-intensive tasks to get their time. And interactive processes, since they have small CPU bursts, we could have a very short time slice, and then we're wasting a lot of time context switching, but the interactive processes fare a little better. So this is round-robin scheduling. Does anybody have questions about this? I know we talk about it in CS124, so it's not new or particularly exciting, right? It's like, okay, great, round-robin, woo! Okay, shortest job first. We also talked about this one. And I have this little note here that, we call it shortest job first in the, in CS24, but really what we're talking about is how long will the next CPU burst be, okay? Because really we expect the program will have multiple CPU bursts. It will eventually block an I/O, and we'd like to estimate, well, how long does it take to get to the next I/O burst? That's really the amount of time that we'd like to estimate. And so this will minimize the average waiting time of processes. So again, we had this example in CS24. If we have 4 processes with these expected CPU burst times, so 2 units, 4 units, 5 units, and 7 units, and we do them shortest to longest, then we get an average wait time of 4.75. And if we order them in the opposite order or any other order that's not shortest to longest, then we see that our average wait time will get a lot longer. So 0, 7, 12, and 16 has a significantly higher average than the shortest to longest ordering. Okay? So that's the idea behind shortest job first. But of course, how do you actually predict the length of the next CPU burst? That's kind of like reading the future, and we have demonstrated in general that we're not very good at that. So we have to basically predict it using past behavior, which is usually a pretty good indicator, but the problem is sometimes we have programs that change their behavior dramatically as they execute. And so we'd like to make sure we don't put too much weight on, distant history, and we'd like to be able to consider recent history a little bit more strongly, like give it a little bit heavier weighting. And so typically you'll see these systems use an exponential average. Okay? Now, when I was staring at my slides this morning, I totally didn't notice the difference between t and tau, and I'm like, why is that even interesting? But tau is very important because tau captures the historical behavior. T is the most recent amount of time that the process ran before it finished. Okay, I shouldn't say process. It was the time of the most recent CPU burst. Let me say it that way. So the process hasn't terminated yet. And so we have this alpha, which is a value between 0 and 1, and it allows us to weight the most recent one and the historical behavior. So we have this nice knob that we can turn and sort of see what do we want to actually weigh. If alpha was 1, we would only look at the most recent. If alpha was 0, we would only consider historical behavior, which I guess would eventually include Tn, because we update tau based on the various, both, basically the whole history of the process's behavior. Okay, so expanding this, tau of n plus 1 is going to be alpha times tau, or Tn, plus 1 minus alpha tau n, and then you can go ahead and expand what tau n would be. And you can see that you get this thing, and if you keep going, then you end up with seeing where the exponential average term comes from. You have this 1 minus alpha, which is, you have the first term is 1 minus alpha. Well, I guess let me make sure that I don't say this incorrectly. So yeah, you have 1 minus alpha, then 1 minus alpha squared, all the way up to 1 minus alpha to the n plus 1. And so you can see it gets smaller and smaller as we shrink that, because alpha is between 0 and 1, that's going to shrink as we get further and further into the past. Okay? And so tau 0 is just the original guess of how long we think the process will take. I don't know how we guess that. I'm sure somebody has some clever thoughts on how to do that, but I didn't bother to read into it. Okay? So, but this is how we can sort of come up with a guess as to how long the process will run for its next CPU burst. Okay, now we can either make this preemptive or non-preemptive. And obviously if it's preemptive, then if some blocked thread or blocked process became ready, so it was blocked and it becomes ready, and it happens to have a shorter estimated runtime, remaining time left to run, then we want to go ahead and bump it to the front of the queue. So it might actually preempt the current job on the processor. Okay, so we call that shortest remaining time first, because the guy who was running will become ready and it will still have some remaining time left. So we put it back into the queue. And of course, we also talk about this in CS124 that shortest job first can have starvation issues if you have long processes and basically short processes keep showing up. So if you have short jobs, I should say that we keep having a process's behavior where it keeps becoming ready quickly, so it keeps having short CPU bursts, and it keeps becoming ready frequently, then it could starve a long-running job from ever actually getting to the processor, which is no good. We want to try to make sure that everybody eventually gets to run, or else you'll have processes that never actually finish. Okay. Now, are there any questions about this? That's basically all I'm going to talk about with shortest jobs first. It's mildly interesting. Thankfully, we don't have to implement it. I don't know, it looks really boring to me to implement that exponential average stuff. But shortest job first is a simple example of priority scheduling. We're actually going to talk about priority scheduling. Like probably the second time I taught this class, people were like, why do you have to why do we have to implement a priority scheduler? Who actually uses priority schedulers? Well, it turns out a lot of space probes use priority scheduling, which we'll talk about. But, priorities are actually important in most of our scheduling algorithms. So it's kind of nice to have a basis of being able to have the simplest kind of priority scheduling as part of your experience. So shortest jobs first, though, you can think of it as being priority scheduling because the shortest job has the highest priority. It always gets the CPU first. But we can also give processes fixed priorities, which is something you all have to do on this project. And typically it's just a number, and of course, should the lower number be higher priority? Should the higher number be higher priority? Well, operating systems have historically been all over the map on that. So I can't remember. I have some examples toward the end, and Linux and Windows, as usual, do it the opposite way of each other. But yeah, you can either have preemptive or non-preemptive priority scheduling, which again, in Pintos, what you have to implement is preemptive priority scheduling. So if we have non-preemptive, then when we get a new high priority process, it does not interrupt the current process that's running. Okay, so that's non-preemptive. Preemptive just means if a new higher priority process joins a ready queue, it gets to go to the front. It gets right onto the CPU, and the lower priority process is bumped off. Okay. Typically, interestingly enough, we do not enforce time limits. So again, I hold the CPU until I yield, block, or terminate. Now obviously, if I yield, then I'm going to get it right back unless there's other processes with the same high priority. Typically, the way these systems work is if you have a bunch of processes at the same priority, it'll just round robin them. So yielding in that context would make sense, but if I'm the only process at the high priority and I yield, then I get it right back. So it's like, okay, that was interesting. So anyway, those are some of the details there. Let's see, yeah, priority scheduling is vulnerable to starvation. Okay, that's by design, so you can design systems carefully and make sure that that doesn't happen. You make sure your high priority processes always eventually block on something, maybe on the timer because they need to wait for something else to happen. There's some interesting approaches that you'll see in people who have implemented priority scheduling. You can age processes, so the longer it's in the ready queue, you just sort of like slowly bump up its priority until it finally is high enough priority that it gets the CPU. So that's one thing you can do to keep starvation from occurring in priority scheduling. And of course, the other one, which we talk about quite frequently, is priority inversion, where you have an interesting situation that can occur where a lower priority process will prevent a higher priority process from ever getting the CPU. Okay? So like I say here, higher priority processes, what's supposed to happen is the higher priority process is supposed to preempt the lower priority process, but we see that not happen. Okay? And this is the classic scenario. You see it in the literature that discusses priority inversion and so forth. So we have a low priority process running and it locks a shared resource. Then the high priority process starts running. It would like to acquire resource R, but it's not able to. So it goes ahead and blocks, and since it's blocked, it's not able to do anything. So we resume L, which would be fine. This, if this were the whole world, then we would just keep running, and eventually L would finish and H would preempt, and off we go. But the problem is, then we have medium priority process M step into the picture and mess everything up. M4 screws it all up. So anyway, M doesn't need R, and it can run as long as it likes because we don't have any preemption in priority scheduling, and so it runs indefinitely, and L is blocked indefinitely, and thereby H is also blocked indefinitely, even though we'd like to actually get H its resource so it can finish. Now, typically, and so the reason why this is actually a problem is because typically high priority processes are given really important things to do. Okay? Some of you may have taken CS124 where I used the Mars Pathfinder problem, and so you'll actually get to see that. We'll talk about that briefly in a moment. But, if they have this situation where the high priority process is taking care of system critical things and then they're starved out by some lower priority process that can run a really long time, then our system can basically fail. Okay, so Pathfinder was, so 1997, that was a year before I was going to graduate college. I was like, it was junior year. I remember it sucked because I was here. So anyway, and Pathfinder got launched, and everybody was excited. Like, what are they, is this thing going to even work? Because instead of, like, having rockets and stuff, we're going to make, we're just going to surround this probe with air balloons, and it's going to bounce all over the surface and then open up, and yay, this is going to be cool. And a whole bunch of people were like, no, it's never going to work. So it was exciting. And so everything worked out how it was supposed to. This thing opened up, and the rover drives off and everything. But then what happened is we started hearing news reports that the thing is rebooting all the time. Okay, well, that's not a good sign. So what's going on? Well, it turned out that it was actually a priority inversion issue on the rover. Okay, you had the high and low priority processes sharing a common resource that they both needed to lock before they utilized it. And the high priority process was responsible for resetting this watchdog timer. The idea behind a watchdog timer is if it counts down to 0, then it reboots the system. And what's supposed to happen, if everything's working right, is periodically some high priority thing goes and resets the watchdog timer so that it doesn't actually hit 0 and reboot the system. That's a way of telling that the whole system isn't wedged. Okay? But if the whole system is wedged, then it's not going to get around to resetting the watchdog timer, and it hits 0, it resets the system, and it comes back, and it's like, oh, I must have wedged myself or something. So that was the idea. But what was happening is the Pathfinder was rebooting all the time. Well, the medium priority process was doing something like weather measurements or sending data back to Earth, which tend to take some time. And it didn't require any locks, but what it was doing was preventing the high priority process from resetting the watchdog timer. And so the thing kept rebooting, and they're like, okay, the thing is only like a few million miles away, so how are we going to actually solve this problem? Okay. Let's see. So I just wanted to mention just a few other details about this. You might say, how could the likes of JPL screw something like this up? And, you know, I don't think that's actually a very fair question because it's surprisingly complex. But the operating system that they were building this on is called VxWorks. Has anybody heard of VxWorks? So it actually is an operating system that is used for a significant number of these kinds of projects. And it has a very simple priority scheduling system for managing multiple jobs. And it has the ability to, you know, have this problem. But it also had a solution implemented which they just left off. And we'll talk about why when we get there. So I'll just sort of use that as setup. Now, various solutions. One is random boosting, which to me seems crazy, but that's what Windows decided to do for the priority inversion issue, which is basically, well, if we have a problem where it's actually, you know, we have a priority inversion, let's just bump up stuff so that eventually it will get a high enough priority that it will get to run again. So basically, it's ready, but it's preempted. Then I'll go ahead and randomly bump up its priority until it exceeds the priority of other things, and then that'll hopefully resolve priority inversions if they occur. Thankfully, I don't think it does this anymore, but that's how it solved these kinds of problems back in the day. You also have another one, which is pretty interesting, a priority ceiling protocol, which is probably the lightest weight approach that you could choose to solve priority inversion, where basically resources are given a ceiling priority, which is the highest priority of anybody that's allowed to lock that resource. So that's the hard part, is figuring out what is the highest priority of any process that can lock this resource. And when a process locks the resource, it automatically gets the priority ceiling for that resource. Okay? Obviously, if you had like 5 resources that you could lock, you lock 1, 2, 3, 4, 5, you get the ceiling, which would be, you know, the highest of all of them. But priority ceiling protocol is really lightweight and really simple. And some of you who have implemented the priority donation mechanism now probably can see how this would be much, much lighter weight to implement. Okay, so priority donation, aka priority inheritance, is the most sort of general purpose, but it's also pretty costly. And so like I say here, if a high priority process is blocked waiting for a resource held by a low priority process, we donate the high priority process's priority to the low one. So that should bump it up over anybody in the middle who's keeping everybody from moving forward. Okay. Now, typically we choose the maximum. If you choose the sum, which is possible, then you can run into issues with having other weird priority inversion issues. So basically, typically the maximum is what is used when you are going ahead and assigning a priority. Okay. Any questions about any of these? All right, so we'll go ahead and keep going. Yeah, priority donation does have some issues. A lot of times you'll have process waiting on process, waiting on process, waiting on process, and you have to go all the way down that chain. Yeah, so 2 locks R2 and then wants to lock R1, 3 locks R3 and then wants to lock R2, and blah, blah, blah. So if process 5 is high priority, then you have to make sure process 1's priority is updated to reflect everybody in between. Okay, So that clearly takes some time. So this is serious overhead. And this is also, as an aside, why JPL left priority donation off in VxWorks when they sent the rover up to Mars. Because they're like, this is a lot of overhead. We've never seen this problem in real life, so maybe there isn't a problem. But, so they don't just turn things on because it might be a good idea, because, when you send a space probe far away, you don't have, you don't want to be taking very many risks. Okay, so this is a huge overhead that can be imposed by having to deal with these kinds of situations. You also have deadlock issues that can occur. And your donation mechanism, it's not like deadlock is okay. Deadlock is still a bug in your system when you have deadlock in these situations, but it causes the failure in a new way. So process 1 locks R1, 2 locks R2. Process 1 wants to lock R2 and block, so it donates its priority to process 2. So far, in our graph of who's waiting for whom, we have no cycles. So that's fine. That's a really quick, simple thing. And then process 2 attempts to lock R1 and blocks. And it's weird because now it sees itself waiting for itself. Okay? So the priority donation mechanism needs to be clever about detecting cycles, or else when you have a deadlock between processes, what happens? Well, instead of everybody grinding to a halt and waiting, now you see spinning in the kernel following the cycle. Okay? So that's no good. And so basically, a priority donation mechanism should also be able to detect deadlocks so that it can actually say, hey, this bad situation came up and y'all are messed up, and so you need to fix your problem, but I'm not going to hang. Okay, so that's kind of the issue that you have when you have a cycle in this graph. You can run into big issues. Okay, any questions on any of these things? I don't think you guys have to deal with that in Pintos. Yeah, which is good. Yeah, did you have a? Yeah, no, I don't think there's any test, right, that actually do that. That would be really awful. I would fly up to the Bay Area and smack the guys that wrote Pintos if that happened. I wouldn't really. I don't want to spend the money on a plane ticket. All right, so enough about priority scheduling. Now, there's a couple of multi-level queue scheduling algorithms that we're going to talk about. One is the one you have to implement, or at least the basic version of it, because we're not going to go into the BSD scheduler because you have documentation for it. But basically, if you look at processes and how they behave, you can kind of categorize them based on what they do. So you have system processes, let's say they're critical things, interactive processes, interactive editing processes. Why would you make that distinction? Well, maybe one, you expect to be getting a lot of input all the time, but editing processes, you expect that the person's going to be staring blankly at the computer at times as well. So maybe a slightly lower priority. And then batch processes as well. So those are CPU intensive. Okay. Now you can also look at them from a standpoint of general categories. So I have things that are occurring in the foreground because they need to interact with the user. We'd like them to be responsive so users don't get angry and throw the computer. And then background processes have large CPU bursts and are not interactive. So this is multi-level queue scheduling. Notice it is not multi-level feedback queues. You'll notice that what we do is we actually assign processes to a queue and then they do not move from that queue. So we just have to pick a queue based on what we think the process needs. So queues have a decreasing priority. The highest priority queues are always going to be pulled from first until all of those processes block, and then we'll go down a priority level and blah, 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 all the way to the low priority queues. Okay. And so you can see that if you do this assigning badly, then you have terrible problems, because if you put a batch process into a system process queue, your whole system suffers massively from it. Okay? And sometimes people would do that. It was definitely possible back in the early days of Windows that you could say this process is super high priority, except that it's computing, and now it's higher priority than the thing that handles the mouse moving. And the whole system is like horribly non-interactive after that. So you could do that kind of stuff. So highest to lowest, yeah, and queues have their own priority. And typically the way this works is if there is a runnable process in a high priority queue, it gets the CPU right away. And again, why do we do this? Because we're trying to maintain responsiveness. We're trying to make sure that critical system tasks happen. Okay, so that's why this is typically a preemptive scheduling mechanism. And the other aspect of this is we expect that the higher the priority, it has to happen and it will be short, so it's not going to hold the CPU for very long, or we expect it's interactive and it's going to block really quickly. So that's why the whole system behavior doesn't suffer when we move these things into the high priority queues. Also, you will sometimes see these multi-level queue schedulers try to subdivide CPU time across different queues. So they sort of say, you know what, we want to make sure that the bulk of our time is spent running from these queues, and then some much smaller percentage will be used for lower priority items. So this is the idea of multi-level queue scheduling. It's kind of like the first come first serve scheduler. It's like, okay, I can see that this is the basis of something else, but by itself it's kind of limited and it's not very effective. Okay, so queues can have their own scheduling algorithms and parameters. So if you had real-time processes, they needed to get real-time scheduled on the CPU so that you could make sure that those things always get to run at a specific time frame. Then you could have a scheduling algorithm for that. I mentioned batch processes. Okay. Anything that doesn't fall into these categories, you might just do round robin from its queue, so that's not a big deal. And the reason why this is lame is because processes frequently change behavior over time. It's not uncommon for this to occur. Now, it's also really common for a process to stay the same all the way along. I suppose something like a web browser would be a great example where virtually all of its life is spent just being an interactive process. Microsoft Word, the bulk of its life is spent being an interactive process. Okay? But then there's plenty of examples of processes that don't behave that way. So MATLAB is a great example. One of my favorite programs ever, right? So I sit there, I write my MATLAB program, and then I run it for 2 hours, and so I walk away and do something else. It switches from being an interactive process into being a batch mode process or a compute-intensive process. Photoshop is another great example. Handbrake, which I use for transcoding the recordings, all of that kind of stuff, interactive, and then it switches over to being compute-intensive. Okay? So multi-level feedback queues are basically multi-level queue scheduling plus the ability to move processes between priority levels. That's really all we're adding here. Okay, and thankfully we already talk a lot about this in CS124, so we don't need to beat it to death. But basically we want to favor the short jobs, the ones that block, yield, or terminate quickly, because we want to make sure that they get the CPU quickly, so we make sure that they get high priority. This will approximate shortest job first scheduling. And if we have processes that block frequently on I/O with short CPU bursts, then we can presume pretty well that they are probably interactive processes. Okay, that's a pretty safe bet. When you press a key, a whole bunch of stuff happens, and then it blocks again on the keyboard. Press a key, a whole bunch of stuff happens, and it blocks on the keyboard again. When you have that kind of behavior, it's a safe bet that it's an interactive process. And so then we can basically separate processes based on their runtime behaviors. Now there's another goal here, which is that we'd like to have few context switches for longer running tasks, CPU intensive tasks, because they hate context switches. So that is also sort of a goal that falls out of this. Thankfully, it's just sort of automatic based on these other goals. Okay, so we have multiple FIFOs for processes. So again, we have a queue for each priority level, but they also have some time limit associated with the queue. Okay. And so what we do is we put a new process. Typically, I shouldn't say the highest priority queue because that may be reserved for system or real-time processes or something like that. But there will be a highest priority queue for applications. We just stick it there. Okay? And it will eventually get to run, and then it'll either be preempted because it took too long, or it'll block on I/O. So then we can go ahead and make our decision about what to do next. So if the process yields or blocks, then it goes to the end of the same queue. If it gets preempted, then it's bumped down a queue level. And if you have a low priority process that is starting to behave like an interactive one, it could be moved up. So if it stays within the time slice, let's say a few times, then go ahead and bump it up to the next queue. So what happens is processes get sorted into queues based on their behavior really quickly. And the queues are prioritized, so now we get a nice system that favors interactivity, favors short CPU bursts, but still will not context switch away from longer CPU burst processes if nobody else is ready to run. So that's kind of the idea behind multi-level feedback queues. Okay, so how many queues to have? That's obviously one option for what do we do for this scheduler. Another thing that's nice that you can tune about it is you can pick different scheduling algorithms for different queues. That's really valuable. Most operating systems leverage that. How do you decide which queue it goes into? Well, like I said, depending on sort of the general category, if it's a system process, it'll go into one set of queues. If it's an application process, it'll go into another set of queues. If it's a real-time process, typically it'll go into a different set of queues. So that's nice. And also these decisions about when to promote and demote, you can come up with clever rules for that as well. So you have all of these options with multi-level feedback queues. And so that's why these are used in most operating systems. Okay, not Linux. Linux is very interesting. One of the things that I really love about Linux, you know, it's just like we talked about read, copy, update last time. Linux is a real tremendous test bed for trying new operating system ideas. And you see that a lot. Let's try a new scheduler. Okay. That didn't work out. Let's try a new scheduler. Okay. And so that's why Linux has actually been through a number of very interesting schedulers that we're going to talk about next time. Same thing with read, copy, update. Let's try this innovative lock-free coordination mechanism. Okay, hey, this is really working. Let's adopt this, and so forth. So it's nice to see that there's places where you can sort of innovate and have a lot of flexibility. Okay, so here's a few details. Windows NT, Vista, and 7. I've been told that 8 and 10 also behave this way, but I can't guarantee it. But you have 32 levels, and you can see that the lower the number, the lower the priority. So 16 to 31 are the soft real-time priorities. OS 10 has, interestingly, 4 priority bands. So it's not quite exactly multi-level feedback queues, but it's along the same idea. So you have normal, system high priority, kernel mode only, and real-time threads is the very highest priority. And the threads are constrained to be within their priority band. So obviously a real-time thread is never going to be demoted into kernel only. That wouldn't make any sense, and so forth. So that is one of those nice things about multi-level feedback queue scheduling. Various BSD Unixes have a lot of queues, various categories. So again, you can sort of pick a category, or I should say you can pick a queue based on the category of process and start it there and retain it in a band if you need to. And Solaris, what's Solaris? Does anybody here run Solaris? Okay, that's okay. You don't really need to. You know, sometimes I say if you haven't done X, then you haven't lived. You can live without running Solaris. That was one of the first operating systems I had to actually program on, so it was kind of fun, but who cares? Anyway, but it also has 170 keys. But you can see how we have these different operating systems that would use these various variants, basically, of multi-level feedback queue scheduling. Very, very popular scheduling. Linux used multi-level feedback queues up to Linux 2.4, and then it started really exploring various things. So what we'll do next time is one of the coolest things that I think scheduling related that you can look at, which is real-time scheduling. We talk about shortest deadline. No, what is it? Shortest deadline? I can't remember exactly what we call it. But anyway, we'll talk about it. Earliest deadline, first scheduling, and how badly it breaks. I can't wait to talk about it. It's really cool. And then we'll start talking about how current Linux schedulers work as well. So we'll talk about that all on Wednesday. I usually have a exam review for Lecture 13 because why not? But thankfully we don't have exams in this class, so we'll get to talk about process scheduling instead. The one thing that we didn't talk about last time at all was real-time process scheduling and the various concerns that you have when implementing a real-time system. And so we're going to spend some time talking about that. I know. Does that power will turn off thing come on often, or should I pay attention to it? Replace lamp. All right, well, we still have another screen, so I guess we'll just forge ahead. Anyway, real-time scheduling. We already talked a little bit about this stuff. We're going to explore it in a little bit more detail today. So we have systems that are driven by specific events, and if we're talking about on the general purpose computer, almost always that's a timer interrupt because I need to draw another frame of my video, I need to play more sound samples, I need to do something like that. Maybe I need to respond to user input. But there's a lot of other real-time systems out there that have a lot of other inputs that they have to respond to. So wheel slippage in an anti-lock braking system would be a good example. If I'm running an assembly line or something like that, I may have optical sensors, I may have actual switches that get triggered at various points, or other things. Cars are getting smarter and smarter. In fact, Google has a car that drives all by itself. And so if some sensor says, hey, you should stop or you should go, then the system needs to respond to that in a specific period of time. So we call that amount of time that it actually takes, the event latency. How much does it take between the input triggering, saying you should do something, to the system actually doing it? Okay, we call that event latency. And just as a simple example, anti-lock braking is surprisingly slow as far as processors are concerned. You have 3 to 5 luxurious milliseconds before the car goes careening out of control. So the ABS system can go ahead and get around to doing that kind of thing. And of course, the other interesting aspect of this is how strict is the requirement of the real-time response. And so you may say that the real-time system is expected to meet all of its scheduling guarantees. It may not be able to, so we might actually have the real-time system say, no, I can't accept this job because I can't guarantee that it will be achieved in the specific amount of time. So it tries really hard as well as it can. Some systems are engineered so that they can't miss, and some allow events to be missed. Okay, so we talked a little bit about this. Hard real-time systems being ones that require events to be serviced within their maximum event latency. Otherwise, the system has failed and typically needs to be reset. Soft real-time systems, if we miss processing an event in time, it's not the end of the world. We just go on and, obviously, typically with a degraded performance. So there are a couple of things. We're going to talk about this whole processing thing because we've already talked a little bit about context switches, interrupt handling, blah, blah, blah. But now we're going to talk about it in the context of real-time systems. So there's 2 latencies that we care about. One is interrupt latency. So some pin on the processor goes high, or maybe it goes low if it's a reverse sense pin, and so now I need to start running some interrupt service routine. So what is that amount of time? We call that interrupt latency. And then there's also dispatch latency. So when I am in my interrupt service routine and say, the wheel is slipping, or some corresponding event, then now I need to switch to the process or switch to the piece of code that actually handles that situation. Some other program may be running. I need to stop it. I need to switch over to the one that should handle this event. So that's dispatch latency. Okay. So we have our tasks. This is a nice little thing, task timeline. The task is running. We get the interrupt occurring, and then we have a whole bunch of stuff that has to happen. First of all, the CPU has to finish whatever it's doing, and that could be long if we're doing a div or something like that takes a while to complete. So clearly, that whole sequence of events has to occur because interrupts are never delivered in the middle of instruction. It's always after an instruction completes and before the next one starts. Of course, if interrupts are turned off, then when I do STI, immediately the interrupts start being delivered. So that may be when the interrupt actually gets handled. So the CPU dispatches, remember, it looks up in the interrupt descriptor table. Okay, here's the address for this. It calls the interrupt service routine and begins executing, and that's going to invoke the operating system interrupt handler, which we already talked about a little bit briefly. We're going to talk about it more next time because we're going to start talking about traps and system calls. We need to save whatever was going on. So remember, we're interrupting a program, probably a user mode process, so we need to save its register state, flags, blah, 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 a few things that weren't actually saved by the processor interrupt dispatch. And so we invoke the interrupt service routine and then carry on. And so that is, yeah, so we're down one screen now. Woo! So that part is the interrupt latency. Okay, the interrupt occurs, and then the CPU goes ahead and dispatches, and then the operating system saves the state of whatever was going on. And then we're in the interrupt service routine. Now, obviously, if you're disabling interrupts a lot, you're going to have a big problem with actually getting events processed quickly. Because if interrupts are disabled, then you're not able to actually service them right away. So typically, you need to make sure that you disable interrupts for as little time as possible. That's kind of a big requirement of real-time systems. I need to always be listening for interrupts because I may need to handle it really quickly. So that's a key detail there. Also, we talked about kernel preemption. We don't necessarily require kernel preemption to implement an operating system that has real-time processes and real-time support. But if we have kernel preemption, then that makes our system even more responsive, because if we're in the middle of kernel code that's not critical, then we can go ahead and dispatch away from it. We can switch away from it and go do something that's more important and then get back to that other kernel thing when we actually have time to, when it's not as critical. So kernel preemption actually really helps a lot with interrupt latency as well. Okay, so that's interrupt latency. Now the dispatch latency, you can see we have our picture gets a little bit more sophisticated now. If you guys' necks start to strain, you can all move to the other side of the room. It won't offend me. So anyway, let's see. So we have interrupt latency, and now we're talking about dispatch latency. And we now need to switch to the process that is responsible for handling that interrupt. Okay, so that's fine. Remember, we had the scheduler and we had the dispatcher. The dispatcher needs to go as fast as possible, but we already needed the dispatcher to go as fast as possible. So that's not a big deal. And there's a few implications which are not like subtle at all. So the first one, real-time processes really need to be the highest priority process in the system, because if we want to be able to preempt whatever's going on, it should be at a lower priority than whatever we're switching to. So that's why, for example, on the Mac, you have real-time processes, and then you have kernel processes are at a lower priority than real-time processes. That was something that was really key because Apple understands that a responsive system makes people happy. And so real-time processes are at a higher priority than even kernel processes. Second one, obviously if a process is running on the CPU and some higher priority process becomes runnable, it should preempt the lower priority process that's on the CPU. Okay? Again, neither one of these is really that subtle. You would probably figure them out really quickly if you were implementing an operating system with real-time support. So I should be able to preempt a lower priority process. This does not imply kernel preemption. Again, all these terms are reused in many different ways. You have threads and kernel threads, and you have preemption on a scheduling front, and then you have kernel preemption. And so just make sure you keep these all straight in your head. We're just talking about preempting a user space process. Okay? And we at least need to support that if we're going to be able to do real-time process scheduling. If we also have kernel preemption, then we're even happier. But these two things are just very basic constraints or requirements of real-time systems. Okay? Now you see that there's a missing box there. Curiously enough, why is there a missing box? We'll talk about that just now. The dispatcher obviously needs to be efficient. We already talked about that. It needs to be efficient anyway, so that's not a big deal. What's more interesting is you may have a situation where some lower priority process is holding on to resources that the real-time process actually needs. Okay? Now that's probably not likely in the computer, our general purpose computers that are sitting in front of us and so forth. But if you're talking about a system like a car that is, has some automation features, it may be that the car computer needs to stop listening to the driver and do something else because otherwise the driver will die. Things like that. So there's situations like that where you may need to grab back resources that some other process is using so that the real-time process can utilize them. And so this we sort of described as resolving resource conflicts. Okay, so if there's anything like that, then we need to handle that as well. And so you can see that all of these things kind of need to happen to get from whatever was happening to the process that's supposed to respond to the real-time event. Okay? I think this is all pretty straightforward. Are there any questions? Okay, so that part, yes. Well, that's what's interesting about it. The operating system can do whatever it wants. It can provide whatever kind of abstraction that it wants. And so it may be that if the user process was doing something, that when it switches back to the user mode process, it receives an error code or something like that saying, sorry, but your thing was taken away from you in the meantime. So you can definitely have situations like that. Now, clearly you would expect that to happen very rarely because it's pretty infrequent that a low priority process would be using the same exact resources that a high priority process would be using, like a real-time process, something like that. But if it were, if you had that situation, probably the two things would know about each other, and so the low priority process could just say, oh, I lost it because some real-time process ran, and I need to restart, I need to retry. Okay? Now that's a very specific example. There's other situations that we will actually talk about pretty quickly. We'll probably talk about them next week because one of the really interesting areas, interesting to me I should say, of operating system implementation actually comes from signal handling. How do you deliver signals to a user space process? Turns out to be really interesting to me and really sophisticated. And one of the things that can happen is a signal can interrupt a system call. So what do you do in that situation? I don't know if, now all of you have actually done a little bit of programming at this level because you wrote the command shell, but I don't know if any of you noticed that one of the error codes that can be returned by some of the system calls is EENTER. Did anybody notice that? One or two of you? So EENTER means that the system call was actually interrupted by signal delivery. The operating system will try to redo things if you have a situation where it's interrupted at a certain point. But beyond a certain point, it'll just say, sorry, I couldn't do it. Because, I was doing this one thing, and then signal came up, and sorry, I just couldn't do it. And so you could have similar situations where an operating system, if it had to handle resource conflicts, could say, yeah, you were holding it, but guess what? You're not now. and have some mechanism by which the operating system can inform the user process that it lost its resource. So you can imagine the Unix model doesn't really provide this in a generalized way. I'm not sure if Windows does because I haven't done enough Windows system programming to tell you that. The last time I did Windows systems programming was back in 2000. That was a long time ago. But you can imagine that a purpose-built real-time operating system might have a way of communicating to processes. Sorry, in resolving conflicts for a real-time dispatch, you lost your stuff, and you have to reacquire it to go on. Okay, so that's the kind of thing that would happen. All right, any other questions? Okay, let's see. So scheduling. This is where it starts to get really interesting. We're going to constrain ourselves right now to periodic real-time processes, which definitely is not all real-time processes. We just talk about what if you see a wheel slipping on an analog braking system or something like that. So clearly there's situations where it'll be more event-driven and hopefully extremely irregular, not something that actually happens on a periodic basis. So, but you expect that real-time processes will need the CPU frequently and on constant intervals. So we say that there's some period P that we need to execute on. We take some amount of time to complete our whatever task we need to do during each period. You'll notice that I have it right at the end of the period because we're saying this is the latest that we can start it and finish within our period. And so that basically gives you this window in which the process must receive the CPU. And so we say that that's the deadline. And it's not really the deadline is really the right side of that little window. We could execute any time inside that window and still finish in time. Okay? And so if we don't finish within that window, then we're sad. We basically have not satisfied our real-time scheduling constraint. I'll say constraint, not guarantee, because we're not guaranteeing this yet. Okay, so some operating systems do require that you state your requirements, because it may be that you're not actually able to satisfy the request. And so the operating system can be clever and think about whether or not it can actually meet the required scheduling deadlines. And if it can't, then it'll just say, no, I can't do this. You'll have to try again at some point when the system is not as heavily loaded. So we call that admission control algorithms, because we simply do not admit processes that we can't have a reasonable chance of meeting their scheduling requirements. Okay? Yeah, and so this is interesting. You'll notice that second to last point, that if the OS can admit the process, it will basically guarantee that it's able to meet the scheduling requirements. Okay? So you'll see this kind of thing on hard real-time systems where you need to know that you're actually going to meet your scheduling requirements. So that's where we would have admission control. Now, even a general purpose system could have some kind of way of saying, you know what, we have too many real-time processes, performance is really going to be bad, I'm probably going to miss a lot of your deadlines, and it would be nice to be able to tell processes, you know, the system is really heavily loaded so that you could tell the user this is a bad idea. But in general, you see this primarily on hard real-time systems. Okay, so one option for scheduling processes that are real-time is called rate monotonic. Okay? This is one of the simpler real-time scheduling algorithms. Basically, you say the shorter your period, the higher the priority is. If you have a long period for execution, so I execute every 5 minutes, I have a low priority. If I have to execute every 5 seconds, I have a high priority because I need to make sure that I get to the processor quickly. Okay. You also require preemption of processes. So if a higher priority process needs to run, then it preempts a lower priority one, and so forth. And we're not going to prove some of the assertions in this lecture. I will point you at other material where it's really interesting. But as far as static priorities are concerned, this algorithm is the optimal algorithm for scheduling real-time processes. Like it says here, if a set of real-time processes can't be scheduled by this algorithm, then no algorithm with static priorities is able to schedule it. Okay? Now, there's kind of an interesting hedge here that you'll notice. We have static priorities, so rate monotonic, we just say shorter the period, the higher the priority, and that priority is fixed. Obviously, it varies based on the period, but that's the only thing that it varies on. And you'll also notice that no other algorithm that assigns static priorities can do better than this algorithm. So that should be a huge hint. Well, maybe there's a giant part of the picture that this kind of algorithm where we only assign static priorities is incapable of handling. We'll talk about that in a second. So low priority processes can be preempted by higher priority ones. So you can have priority inversion with this, which is kind of interesting, but we're not going to go into those kinds of situations, thankfully. So the real question is, can you actually schedule a set of real-time processes? So we say that they have a period, and they have a certain amount of time that they take. We call that T. And it's a CPU burst, obviously, because if we have to do I/O, then the process is going to block anyway. But it needs to perform some CPU burst of a certain length during each period, and then it will have met its deadline. So here's our example. We have two processes, one with a period of 50 clocks and the other one with a period of 100 clocks. And P1 has a CPU burst of 20 clocks, and the other one has a CPU burst of 35 clocks. Can we schedule these? Well, thankfully we can just sort of simulate this in slideware and we'll see. So you see P1 has to execute on a certain period. P2 has a period that's twice as long, so it executes half as frequently. P1 has a higher priority than P2. So they can start executing at the same time at the beginning. And again, this is where you notice that, okay, we had our deadline and it was a window. So what we're going to do here is we're going to start executing as early as we can within our window to try to get done as soon as possible so that we have no chance of missing our deadline. So anyway, P1 and P2 can start executing at the same time. But who gets to go first? P1, because it's the higher priority. So it runs. And remember, it had a CPU burst of 20 clocks, so it goes ahead and finishes. So then P2 starts, and it takes, how many do we have here? 10, 20, 30. But you'll notice something interesting. Remember, it takes 35 clocks to finish. But at the time we hit P1's deadline, then a new window opens for P1. So P2 gets preempted again before it actually finishes. Okay? And P1 finishes because it only takes 20 clocks. P2 is then able to finish its task. Are we happy so far? Yeah? I mean, at least in the context of scheduling we are, right? So P1 has been able to run twice in 2 periods, so that's good. P2 has been able to run once in 1 period. Everybody's met their deadlines. We're happy. And so this mechanism, this process can just repeat itself again. P1 runs, finishes, P2 starts to run. In the process of P2 running, it's P1's turn again, so it preempts P2. It runs to completion, then P2 finishes its last little 5 clocks of CPU burst, and everybody's happy. We meet our deadline. Right? Everybody with me? Okay. So you can see that we have time left over. So you might say, hey, you know what? We could either add more processes, or we could go ahead and have longer CPU bursts for these things. We have a couple of different options. So we can actually quantify this as the CPU utilization. So we just say, how much time do you require over what is the period? And so you can see here that P1's CPU utilization is 20 clocks over 50 clocks, or I need 20 clocks out of every 50. And so you can say that I need 40% of the CPU time. So that's the CPU utilization of P1. Do the same thing for P2. I need 35 clocks out of every 100 clocks. So my CPU utilization is 35%. Now, presumably, we can't get over 100% CPU utilization, right? So 0.4 plus 0.35 is 0.75. That's definitely less than 1. So we should be fine. So the question is, can we actually use our CPU utilization to tell if a set of real-time processes can or cannot be scheduled? Okay. Add up the CPU utilization of all of our processes. If it's less than 100%, then yay, we can schedule it, right? That's the idea. Well, we take another example where, again, we have P1 taking, well, actually, you can see now that P1 takes a few more clocks. Now it takes 25 instead of 20. And it still has a period of 50 clocks, so that part at least is the same, but it has a slightly higher CPU utilization. P2 now has a shorter period and the same CPU utilization. So now P2 is, I'm sorry, not CPU utilization, the same CPU burst size, because its utilization is actually going up. I have to be careful about these terms. So P2 has a period of 80 clocks, and it still takes the same CPU burst. So these are our deadlines now. P1 has a deadline at 50 and 100 and 150 and so forth. P2 has 80 and 160 and 240 if we drew that, but we don't. And again, we compute the CPU utilization. P1's utilization is 25 clocks over 50 clocks, or 0.5. And P2's CPU utilization is 35 clocks over 80 clocks, so that's around 0.44. You can pull out your calculator if you want to see the exact amount. And so we see that the CPU utilization is actually under 100%, so we think, yes, this is good, I can do it, right? But this is where we start getting sad, because if we actually tried to do this in a real system, we would start to notice that we will fail. It is not possible to execute these processes and have them always hit their deadlines if we use rate monotonic scheduling. So again, fixed priorities for these real-time processes. So again, we simulate it in our slideware. So P1 and P2 can both run at the same time. So P1 gets to run first, and it runs, and it obviously meets its deadline. P2 gets to start executing. But then we enter P1's window again, so P1 preempts P2. After P2 has only run for 25 clocks here, so we still have another 10 clocks that we have to complete. So P1 runs, P1 is happy, it runs to completion because it's highest priority, and it's going to hit its deadline. But now notice we only have 5 clocks left to get 10 clocks of work done. So P2 is going to miss its deadline, which makes us sad. Okay? Well, I mean, I suppose specifically it makes P2 sad. Okay, so it's interesting that in this situation, even though we have a CPU utilization that's less than 100%, we still can't guarantee that these processes will all hit their deadlines using rate monotonic scheduling. Okay? This is a pretty interesting result. And it was actually quantified. There were a couple of people. Let me go ahead and throw this up here in a second. But there was a paper that was done by a guy at MIT and another guy at JPL, because obviously JPL cares a lot about being able to schedule real-time processes for spacecraft. So if you have n real-time processes, the CPU utilization has an upper limit that is not 100%. And this is the specific expression. So n times 2 to the 1 over n, or I guess just what, the nth root of 2, minus 1. And so for 2 processes, the utilization has to be less than 0.82, which you will notice was, our first example was below that. It was 0.75, so we knew that we could hit it. Okay. For our new one, we have 0.94, and that's definitely higher than the limit, so we cannot schedule it using rate monotonic scheduling. And if n gets large, the CPU utilization goes down to about 0.69. Where if you have a CPU utilization larger than that, then you can't schedule all those real-time processes. Which is wild, because what we're basically saying is our CPU must sit idle for at least 30% of the time if we're going to schedule all our real-time processes correctly. Okay? Or for 2 processes, the CPU has to sit idle at least 82% of the time if we're going to be able to schedule our real-time process. That's kind of wild. So the specific paper, if you want to look it up, scheduling algorithms for multi-programming in a hard real-time environment, way back in 1973, before any of us here were born. They had figured this out. Okay, so that's rate monotonic scheduling. And like I said, it is the optimal algorithm, or it is an optimal algorithm for static process priorities. Earliest deadline first is a different algorithm. This is actually the one that we talk about in CS124, and there's kind of a reason why. Basically, we set process priorities based on how close their deadline is. Whoever has the closest deadline has highest priority because they're in the most danger of missing their deadline. Okay, this is the way that students schedule completion of homeworks. Probably not a good idea, but anyway, it's a really interesting algorithm because it actually doesn't suffer from this limitation of rate monotonic scheduling. Okay, so processes have to state their deadlines to the scheduler. Okay, and this is the same example as before. So P1 has a period of 50 clocks, CPU burst of 25 clocks. P2 has a period of 80 clocks and a CPU burst of 35 clocks. This diagram gets a little bit more complicated. I apologize. It's just hard to draw. So you have P1 and P2. These are their requirements. And so P1 has the earliest deadline. Remember, P1 and P2 are both in their window. They can both run, but P1 is closest to its deadline, so it gets to run first. and it completes. Now P2 starts running, and we hit the point where P1's window opens again because we passed 50 clocks, and now P1 has to finish before we reach 100 clocks. But now we have two processes, P2 for its first deadline and P1 for its second deadline. So you see that P2's deadline is still closer. So P2 is still higher priority at this point. So it gets to run to completion. P2 is now happy. It's like, I've hit my deadline, yay. But we're still inside P1's window, so P1 starts executing. Let me see if I have this. Yeah, so P1 starts executing because P2's deadline is now way off at 160. P1's deadline is 100. So P1 runs to completion. P2 again begins running because we're in P2's window. So we're trying to get work done before we hit clock number 160. And then we enter P1's third window. Now, where does P1's third deadline sit? 150, right? So we have 160 for P2, we have 150 for P1. P1 should now be highest priority. So see, we enter P1's window, but P1 is closer to its deadline than P2 is, so we can go ahead and preempt P2 and start running P1. So P1 runs to completion for its third deadline, and then P2 gets the processor back and runs until it completes. Because we haven't actually, so P2 gets to complete before it actually, before P1's window opens again. All right? And so forth. Once you finish here, P1 will run next because P1's next deadline is 200. P2's next deadline is 240. So P1 gets to run next, and it'll run to completion and so forth. You can sort of just imagine how this will all play out. Okay? Any questions? But you can see that earliest deadline first changes priorities based on who's closest to its deadline. And we've already demonstrated that this is superior, at least in this specific case, to rate monotonic scheduling, because it's able to schedule something that the other one wasn't able to. But that's what's interesting about it. Okay, like I say here, it doesn't actually have the same requirements as rate monotonic. Rate monotonic required that we actually have periodic processes. This one we really only require that processes say when they need to run. So that could be, I just need to run at this point as a one-shot. Or maybe I need to run at this point and then I have another deadline a little further out and then I have another deadline a little closer. So you could state those kinds of requirements and you could use earliest deadline first scheduling to handle those situations. Okay, so that's kind of neat. Also, earliest deadline first is theoretically optimal, which means that if you have a set of processes, set of real-time processes, whose CPU utilization is, you sum it up and the utilization is under 100%, it can schedule it. Yay! So that's already way better than rate monotonic scheduling. Of course, we had all those other things that have to happen when we get a real-time event and we have to dispatch, so that is overhead. And that imposes a limitation where we typically can't actually achieve 100% CPU utilization. Remember that CPU utilization is computed from the process behaviors, not from all of this dispatching as well. So this is the most obvious example where all of these other details are overhead for the operating system. Okay? But it's pretty neat. Any questions? Any questions on real-time scheduling? This is all that we're going to talk about with real-time scheduling. You may be happy to know that it never makes an appearance in CS124 beyond this lecture. So it's not something that you have to implement, but it's kind of nifty stuff. I think it's really neat. And it's really interesting that you have these various approaches, and they have these subtle limitations that are not obvious at first. And you kind of have to tinker with various scenarios before you really are able to discover and quantify their limitations. We'll see similar issues when we get into page eviction policies. It turns out that certain page eviction policies have unusual characteristics And then other ones don't have those characteristics. And so there's kind of categories or classes of solutions with different strengths and weaknesses. So we'll talk about this kind of thing again in the future, but this is basically all we're going to talk about when it comes to scheduling real-time processes. Okay, last two things that I wanted to talk about today are actually, I don't know if it's right to say, yeah, I think it's right to say two things. We're going to talk about two different schedulers used in Linux. Okay, one of the things about Linux being developed by engineers all around the world as an open source project is that you see a lot of experimentation, and typically it's a very good thing because you get to explore ideas and whether or not they're good. And so Linux 2.4, we'll start there because you have to understand the Linux 2.4 scheduler before you get to the current scheduler. But basically time was divided into epochs or epochs, depending on how you like to say it. It's kind of like tuple and tuple. So I like to say epochs now, but that's probably not entirely correct. Whatever. So basically at the start of each epoch, you have priorities assigned to all of the processes. Okay? And those priorities are based on previous behavior. So real-time processes obviously are going to be the highest priority, and those are absolute priorities because we need to make sure that they stay high priority. Interactive processes have a dynamic priority based on how they behave. So I'm relinquishing the CPU all the time. I'm getting blocked on I/O all the time. Good, you get to have a high priority. And then batch processes or processes that get preempted all the time, it's like, get off the CPU already. Then those are the ones that get the lowest priority. And the Linux scheduler would compute a time quantum for each process based on its priority. Okay? And so basically, the higher the priority, the larger your time slice was, which is kind of interesting because you kind of think, okay, these batch processes or compute-intensive processes probably should have a large time slice since they're low priority. But basically, when you use up your time quantum, you're preempted off the CPU, and the scheduler decides what to do with you. So that's the basic idea behind the Linux scheduler. You can see it's kind of like some of the things we've seen. It's kind of like priority scheduling. Kind of has similar characteristics to multi-level feedback queues. So this is what would happen. The scheduler would iterate over all the processes that were on the system, and it would compute some goodness metric, which is kind of interesting. It was just some heuristic that the engineers came up with to say, this is how good we think you are. Okay? And I have this interesting little note here. If you had a process that had previously run on the same CPU that the scheduler was now running on, you got a little bump up in your goodness. Why would that be? Well, probably because there's some of your data or some of your code still in cache. So if I switch back to you, the system will probably run a little bit faster. So you get a little bonus in your goodness. Okay? And so whatever the best process was, the goodest one, would get the CPU and it would get to run. Okay? And so part of that was obviously the priority of the process. And so if you have a high priority process, its goodness is going to be higher than some batch mode process. And so it would get to preempt other lower priority processes, and it would go ahead and get the CPU. Okay? And you can see that you have preemption as well. Now basically this would happen where all the processes would run, they would each one use up their time that was given to them. So that means all the high priority processes, they'd have a big time quantum. They would get preempted all the time, so they'd run, they'd do their little CPU burst, and then go back to blocked, and then they'd run again, and go back to blocked until all of their time quantum was consumed. The low priority processes would run and probably have to be preempted at the end of their time slice, and then they'd be bumped off the CPU. So all the processes get all of their time, and then the current epoch is up. Okay? So you'll notice that a process can be scheduled multiple times on the CPU. I'm a high priority process, I get preempted a lot, I get on the CPU a lot. Okay? No big problem there. If I'm a low priority process and I get preempted by high priority processes a lot, well that's okay. It'll eventually come back to me and I'll get to run a little more, and when my time slice is up, then I have to wait till the next epoch. But you can see that processes would get to hop on the CPU kind of frequently, which is an unusual characteristic of the Linux 2.4 scheduler. So what happens at the end of the epoch? Well, we go through and compute goodness for everybody. We compute everybody's priority. We update everybody's priority. So you were high priority and you've been preempting a lot, or you used up your time slice a lot. You didn't actually do a lot of I/O. So your priority gets decreased. So now you are going to be less good. You're now a slightly bad process. Okay? You have some batch process or compute intensive process and it starts blocking on I/O a lot. Then you say, you know what? You should get a little bit more goodness. And thereby you'll also receive a larger time slice. Things like that. So this is what would happen at the end of each epoch. And so what they noticed, and you could probably notice this yourself if you just think about the problem a little bit, is that you've got all these sweeps through all the processes. At the end of each epoch, I have to go through all the processes and recompute a priority for them. Every time the scheduler runs, I go through all the processes and figure out which one is goodest. And then I run that one. So this is kind of lame. And you could see that this would not scale very well as you get a large number of processes. So the Linux 2.6 scheduler was completely rewritten. It would still use the 2.4 approach, but it was rewritten in a way that would make it as efficient as possible. And so we ended up with the 01 scheduler. Whoever creates these schedulers clearly has a gift for naming them, because you think, 01 scheduler, wow, that's got to be the best possible scheduler. So that must be one that we want to use. Okay? But now, instead of actually doing these things in a very formal, let's go over all of the processes at once, it's now sort of done in a more incremental way. So now we have a priority array, which is very similar to our multi-level feedback queue mechanism. Okay? Each priority level has a queue of processes. You can see the highest priority, or I should say the second highest priority has 2 processes at that level. The fourth from the bottom has 2 processes as well. And we also have a bitmap that tells us which queue has processes. So that we don't even have to look through, like iterate with a for loop over our array of priorities and say, okay, do you have a null? Do you have a non-null? Which one is best? You can just use the bitmap to figure out which process, I should say which queue has processes in it to start running. So that'll be a little bit, you use your bit manipulation magic to figure out that. Okay? And so basically finding the highest priority process to run is a constant time operation. Now it would still be constant time if you have a for loop, because you're looking at the priorities. You're not looking, you're not iterating over all processes. So you have a fixed number of priorities, and so you're still going to have a constant time operation. But you can even make the constant better. It's like, if we say it's order n, then it's still constant times n. So let's make the constant smaller, and we're happy. So we try to find the index of the lowest one in the bitmap, and then use that to access our priority array. Okay, seems fast so far. There's 2 of them. Okay, we have the one for the current epoch, and then we have one for the next one. And so the active array is going to be processes that still have some of their time slice left. And then the other priority array is processes that have consumed their entire time slice. And so when we have a process consume its entire time slice, you can probably guess exactly what happens. We move it to the expired array, but we also compute its new priority. So it just goes ahead and slots over into the new place. Okay? This guy maybe stays at the same priority. I don't know why I animated this all, but there you go. Okay? Yay, slideware. Okay? So you can see that we're sort of doing this incrementally. We're spreading out the cost instead of doing it all at once in a very inefficient way. When the active priority array is empty, our bitmap becomes 0, then we know that our current epoch is over and it's time to switch to the new priority array that we just built out. Okay? Because now expired becomes active, active becomes expired, and off you go. Okay? So, same approach as Linux 2.4, but written in a much more intelligent way. Okay? And so that stuck around until Linux kernel 2.6.23, because I know you probably care about that number. We're already like up to what? I can't remember what the current Linux kernel is, but we're way past that now. But yeah, the problem was that the order 1 scheduler was still really kind of convoluted, and there were a lot of parameters, like what should be, the minimum time slice that we give to batch processes, what's the maximum time slice we give to interactive processes. There's this weird relationship, if I give batch processes too large a time slice, then all my interactive processes start to stutter when their time slice runs out and the batch process gets to run for a really long time. So there's all these little weird things that you have to tune for the O1 scheduler. And so people didn't like it. There would always be, somebody says, well, let's make this little change, and then all the interactivity tests on Linux would just dive because they thought, okay, this is, seems like a reasonable change, but then it was sort of very unstable, and you couldn't always predict the results. And so if there was a scheduler name that was better than O1, it would be completely fair scheduler, right? Okay, this should be the last scheduler we ever used because obviously every other scheduler was not completely fair or something. So, but anyway, now we have the completely fair scheduler in Linux. And I think it may actually still be used. I'd have to look that up. But the completely fair scheduler has a very different approach to how processes are scheduled. Okay? And you'll see this notion of a fair share described a lot when you read about the completely fair scheduler. Basically, that's dependent on the process's priority. Okay? So if I have a high priority process, it should get a larger share of the processor. If I have a lower priority process, it should get a smaller share of the scheduler. I mean the CPU. Okay? So what happens is each process has a virtual runtime. You guys already have your timers and stuff. You can imagine in your Pintos kernel thread implementation, every time you switch to a kernel thread, you start counting how much time it gets to run. Okay, so that's an actual system clock saying this is how much time the process has run for, and you can update that relatively easily. I don't think you have to do that. It may already be taken care of for you. Maybe it's not because your scheduler doesn't care. But yeah, so that would be the way that that's done. But the virtual runtime is a little bit different. It's not the actual system time. Basically, the virtual clock is scaled so that higher priority... This is wild. It's like relativity in the operating system. The higher the priority of the process, the slower its clock runs. The lower the priority of the process, the faster its clock runs. So that lower priority processes run out of time faster than higher priority processes. Okay? So that's pretty wild. Now, the other thing is that since a high priority process is going to be preempted a lot, its virtual clock is also going to run slower because of that. So I'm running, my virtual clock is moving, I stop running because I do something that blocks, and now my virtual clock stops running. So my clock keeps staying really slow. Now you have all these processes that are ready to run, and they each one have a virtual clock that's ticking up from 0 when the process was started. And they're maintained in an ordered tree. So that the bottom left process always has the lowest virtual clock. That's the one that gets to run. Like I say here, it's log n to insert a process into the tree, so it's not as good as the O1 scheduler anymore. But anyway, that's the one that's run for the shortest amount of time, therefore it should get the CPU first. That's the notion behind the completely fair scheduler. Any questions? They seem to like it. It seems to do pretty well. Let's just wrap up our discussion pretty quick. So obviously when you have some kind of tree structure and you want to keep track of something that's way down deep in the tree, well, there's easy ways of keeping track of that so that you can actually hold that in a separate variable, and then it becomes very easy to look it up. So, so that's O1 for looking up a process to run, but when you modify the tree, that's typically a log n operation. So yeah, time quantum is based on the targeted latency. So this is the other thing that's really interesting. The time quantum is sort of picked system-wide. So the targeted latency of the system, how quickly should every process get the CPU? The total number of processes in the system, which obviously if the total processes goes up, each process should get a smaller slice, but then you have a minimum amount that everybody must get. And so basically using that global thing, that global time slice size, And everybody's virtual clocks, where everybody's clock runs at a different rate based on the process's priority and how often they block, that's how the Linux scheduler decides who gets the CPU next. Okay. So here are the general behaviors. So processes blocking or yielding frequently, they have lower virtual run times because they're not getting to run. Their virtual clocks aren't progressing. And so they end up leftmost most of the time because their virtual clocks are very low, and so they get the CPU really quickly. So that's a good thing. If you have a process that's running and completing its time slice all the time, well, its priority is going to stay low, and so its virtual clock is also going to be very high. It's going to run faster, so it'll be at the right side, and it will be preempted by higher priority processes that become ready to run. Okay, so that's kind of an interesting thing. I love that people are experimenting with this kind of stuff. So just keep that in mind. Linux is a great test bed if you have interesting scheduling ideas that you want to experiment with. And I believe that they also have a pretty good test bench for measuring process interactivity and process responsiveness so that they can, because if they're experimenting like this, clearly they need some way of actually quantifying whether it works or not. Okay. Anybody have any questions? Alrighty, so just as a last thing to mention, Stride scheduling, I'm going to give a little shout out, I guess, to Stride scheduling, which you may or may not have seen on a CS124 exam. I like Stride scheduling. I like lottery scheduling, are both really interesting, different approaches, so there's a paper about that. And what we'll do next time is start talking about system calls to get ready for the 4th project. So we'll see you all next time.